At this very moment, 4 whole groups of galaxies are crashing into each other almost 6 billion light-years away in a collision so strong that it bends light itself. This part of the universe, which is called MACS J0717, is not a quiet place. It's a battleground where galaxies, plasma and dark matter are crashing into each other at thousands of kilometers per second. Astronomers say it's one of the messiest places they've ever seen in deep space. The gravity, heat and motion are so extreme that no lab on Earth could ever repeat them. The discovery of the cosmic collision zone. The cosmic collision zone story began with a faint shimmer in the sky. It was a place where galaxies were warped and light was spread out in a way that didn't quite follow the normal order of the universe. Astronomers first looked at it with the Hubble Space Telescope and the Chandra X-ray Observatory in the early 2000s. They saw something very strange. Not just one cluster of galaxies, but several of them crashing into each other in deep space. At first, it looked like a smudge in the constellation Auriga, which is about 5.4 billion light-years away. But it turned out to be a huge theater of cosmic violence, a structure so big and rough that it didn't fit the patterns scientists had come to expect from the beginning of the cosmos. Hubble's deep optical images revealed arcs and streaks of distorted galaxies, clues that hinted at a powerful gravitational field bending the light of even more distant objects behind it. That warping effect, called gravitational lensing, was the first major clue that the region was home to enormous quantities of matter, not just stars and gas, but vast halos of invisible dark matter acting like magnifying glass lenses in space. Meanwhile, Chandra's X-ray vision told a different but equally chaotic story. It showed a ghostly blue glow, spreading across millions of light-years. The light of superheated plasma at temperatures exceeding 100 million kelvins, hotter than the cores of most stars. The heat and shape of that glow could only mean one thing. Galaxies and their gas clouds were smashing into one another at incredible speeds, releasing energy on scales never before measured in a cluster merger. Follow-up observations confirmed that this was not a simple two-way encounter. Instead, astronomers identified 4 distinct subclusters, each the size of a massive galaxy cluster on its own, converging in a gravitational pile-up that had been unfolding for hundreds of millions of years. In other words, this was not just a collision, it was a 4-way cosmic traffic jam, a rare and violent snapshot of structure formation still in progress. The discovery offered scientists a live laboratory to watch how the universe assembles its largest structures by merging smaller ones in titanic bursts of energy. The exact coordinates, right ascension 07H17m and declination plus 37°45, gave it its technical designation, but among astronomers it quickly earned a more vivid name, the Cosmic Collision Zone. That nickname stuck, appearing in NASA press releases and Chandra briefings describing it as one of the most complex and chaotic collisions ever seen. It also became a benchmark for studying how galaxies evolve under extreme stress. Within this cluster, the normal rules of galactic life, steady growth, slow rotation, quiet star formation, break down completely. Gas is stripped from galaxies, stars are flung across intergalactic space, and new magnetic fields are forged by shock waves moving faster than sound through superheated plasma. Since then, every camera that has looked at this area, from Hubble to ALMA and the Very Large Array, has found more layers of chaos and complexity. In visible light, it looks like a web of tiny galaxies that are moving around. It shines with the light of destruction in X-rays. It hums in radio waves with the energy of relativistic particles sped up to almost the speed of light. All of these points of view have made the Cosmic Collision Zone one of the most studied and interesting places in the universe. It is a perfect storm of gravity, motion, and energy that is still changing shape today. The meaning behind the name. The label J0717.5 plus 3745 looks more like a computer code than a space address to people who are not into science. But in the language of sky maps, those numbers tell you everything you need to know about the cosmic collision zone, which is one of the most unstable places in the universe. Huge Cluster Survey, MACS, is the project that the name comes from. It is run by scientist Harold Eberling and his team at the University of Hawaii. The study began in the late 1990s and used powerful space cameras to find the farthest and densest galaxy clusters that had ever been seen in X-ray light. Each finding wasn't given a fancy name. Instead, it was given a precise number series that showed where it was in the sky, along with its right ascension and declination. That's where J0717.5 plus 3745 comes from. It translates to right ascension 07 hours, 17.5 minutes, declination plus 37 degrees, 45 minutes. It points to a small patch of sky in the constellation Auriga, visible only through advanced telescopes, and yet holding the mass of thousands of galaxies. Behind that simple code lies a scene of staggering violence. 4 separate clusters colliding in a volume of space about 13 million light-years across. The official designation might sound sterile, but to astronomers it has become shorthand for one of the most important and dynamic laboratories in modern astrophysics. Every part of the name tells a story about how astronomers organize chaos. The MACS prefix connects it to the survey's goal, finding massive clusters that could act as natural gravitational lenses. These clusters bend light from galaxies billions of light-years behind them, creating distorted arcs and magnified reflections that allow scientists to peer deeper into cosmic history. J0717 identifies this particular region as one of the brightest and most powerful lenses ever discovered. Its gravitational field is so immense that it can magnify galaxies from the first billion years after the Big Bang, turning this violent battlefield into a tool for studying the birth of the earliest galaxies. When the discovery was first announced, scientists struggled to describe its complexity. Most known cluster mergers involve 2 main bodies, an incoming cluster and a target. But this one showed evidence of 4 distinct subclusters, each moving at thousands of kilometers per second. Radio and X-ray data revealed intricate shock fronts, while optical imaging showed streams of dark matter and galaxies twisting around one another. As data poured in from Hubble, Chandra, and later ALMA and the Very Large Array, researchers realized this wasn't just another merging cluster. It was something fundamentally new. The nickname Cosmic Collision Zone began appearing in conference talks, documentaries, and NASA briefings, reflecting the awe it inspired in those who studied it. The technical name and the informal one coexist, one for the catalogue, the other for the imagination. The formal coordinates ensure scientists can precisely locate and track it in the vast digital sky. The nickname captures what words like J0717 can't: the raw intensity of 4 massive galaxy clusters colliding, the searing heat of plasma, the bending of space-time, and the strange beauty of destruction on a cosmic scale. In both senses, it stands as a bridge between data and wonder, between the mathematical precision of astronomy and the visceral reality of what those numbers represent. This dual identity is fitting because the region itself embodies contradiction. It is both violent and creative, destructive and illuminating. While the collisions tear galaxies apart, they also light up the universe in X-rays, radio waves, and gravitational lensing arcs, revealing processes that would otherwise remain invisible. The cold precision of its designation hides a furnace of activity beyond comprehension. Scale of the collision. A lot of the time, when scientists talk about the cosmic collision zone, they use similarities that are hard to picture. There are so many galaxies in this area that it takes light more than 13 million years to travel from one end to the other. To give you an idea of how big that is, the Milky Way would cover an entire city if it were a coin. It is one of the biggest and most powerful crashes that has ever been seen. It is a real heavyweight in the universe's order of matter and motion. Inside this enormous battlefield are thousands of galaxies, each containing billions of stars. Yet even these galaxies are not the main players. Most of the cluster's mass comes from dark matter, an invisible gravitational skeleton that outweighs all the stars and gas combined. The hot plasma between galaxies, which glows brightly in X-rays, accounts for most of the visible matter. When the four subclusters collided, their gas clouds smashed together with enough force to heat this plasma to temperatures above 100 million kelvins, hotter than the cores of the most massive stars. This makes the region one of the brightest X-ray sources in the observable universe. But measuring such extremes isn't easy. Astronomers use a combination of gravitational lensing, spectroscopy, and computer simulations to reconstruct what's happening. By tracking how light bends around the cluster, scientists can map the total mass, including the unseen dark matter, while X-ray data from Chandra pinpoints where the hottest gases lie. Together, these techniques reveal a structure unlike anything else in the sky, a tangled web of filaments, bow shocks, and turbulent eddies extending millions of light-years into intergalactic space. The entire scene is a study in cosmic scale, so large that even our largest telescopes can only capture fragments at a time. The kinetic energy of this collision is almost beyond comprehension. Each subcluster weighs several quadrillion times the mass of the Sun, and they're moving relative to one another at speeds exceeding 3,000 kilometers per second. The total energy released when they collide is equivalent to trillions of nuclear bombs detonating every second for millions of years. Yet because of the enormous distances involved, all this chaos unfolds in slow motion. What we see through our telescopes today is the sum of events that have been playing out for hundreds of millions of years, and will continue long after humanity is gone. At this scale, even light bends and time stretches. The gravitational field of the cosmic collision zone acts like a natural lens, distorting and magnifying galaxies that lie far behind it. This effect lets scientists look farther into the universe's past, catching glimpses of infant galaxies from less than a billion years after the Big Bang. In a way, this violent collision has become an unexpected window into cosmic history, a disaster that also serves as a telescope. Astronomers often compare this region to the famous Bullet cluster, another site where two clusters collided and revealed the separation between dark matter and normal matter. But the cosmic collision zone goes far beyond that in complexity. Instead of a single impact, it's a four-way convergence, a turbulent knot where gravitational forces overlap and ripple like waves on an ocean. The result is a kind of cosmic anatomy lesson, showing how galaxy clusters merge to form even larger structures, superclusters that define the skeleton of the universe. Measuring the mayhem. To try to understand the cosmic collision zone is like looking at an event that has been stopped in time. Each picture and each wavelength tells a different part of the story, but all of them together make one of the most complete pictures of violence in the universe ever put together. Astronomers had a hard time not only catching it, but also figuring out what they were seeing. This area doesn't follow easy geometry or symmetry that can be predicted. It's a tangled mess of gas, dark matter, and galaxies moving in different directions. How do you measure that much chaos? The answer came from a combination of multi-wavelength astronomy and some of the most advanced analysis techniques in astrophysics. Each telescope contributed a piece of the puzzle. The Hubble Space Telescope provided crystal-clear optical images showing the visible galaxies and the distinctive arcs of distorted light. Signatures of gravitational lensing. The Chandra X-ray Observatory mapped the searing plasma between those galaxies, revealing where the collisions were most intense. Meanwhile, radio telescopes like the Very Large Array, VLA, traced invisible shock fronts, detecting faint radio waves produced by electrons accelerated to near light speed. Each dataset overlapped with the others, painting a three-dimensional map of an event that spanned millions of light-years and billions of years of time. Gravitational lensing became the key that unlocked the structure. By analyzing how the cluster bends light from galaxies far behind it, scientists could infer the distribution of mass, including the unseen dark matter. Regions where light was most distorted pointed to dense gravitational wells, the invisible skeleton of the collision. These maps revealed something astonishing. The cluster's mass wasn't concentrated in one center, but spread across 4 main cores, each with its own trajectory. That meant 4 independent subclusters were merging at once, an almost unheard of configuration. To confirm this, astronomers compared the gravitational maps with X-ray data. In most clusters, the peaks of X-ray emission, where gas is hottest and densest, line up with the mass peaks traced by dark matter. Here, they didn't. Instead, the X-ray peaks were displaced, often trailing behind the dark matter cores. This mismatch is a smoking gun for active collisions. It happens because the dark matter and galaxies pass through each other easily, while the gas slams together and slows down. The result is a literal separation of matter and energy, captured in motion across millions of light years. But even with those maps, there was still a missing piece: motion. Knowing where everything is doesn't reveal where it's going. To solve that, researchers turned to spectroscopy, measuring the redshift and blueshift of light from individual galaxies. By seeing how their light stretched or compressed, they could calculate how fast each part of the cluster was moving toward or away from us. The results were staggering. Some subclusters were traveling at over 3,000 kilometers per second, confirming this was one of the fastest and most energetic cluster mergers ever recorded. Such complexity was hard to model, even with the most powerful computer programs. Researchers had to make dynamic, multi-body models that took into account the viscosity of gas, the chaos caused by magnets, and the effects of gravity on scales bigger than galaxies. Supercomputers were used to play back the crash in slow motion and match it to data from Hubble, Chandra, and radio arrays. Each simulation took weeks to run. In the end, they had a map not only of space, but also of motion, a live model of chaos that had been frozen in time. The temperature of chaos. For the first time, scientists were shocked by how hot the cosmic collision zone was. Its plasma between the groups that were clashing wasn't just warm, it was flame hot, with temperatures of over 100 million kelvins. This is a lot hotter than the center of the Sun, most stars in the Milky Way, and any explosion on Earth could ever reach. It wasn't a friendly meeting of worlds. Nothing else can compare to the size of that oven, where matter is heated to its very limits. The heat comes from violent motion. As the 4 clusters slam together, their intergalactic gas clouds crash and compress, converting kinetic energy into temperature. Each collision sends shockwaves, cosmic sonic booms, ripping through the plasma at thousands of kilometers per second. These shocks act just like the ones produced when a supersonic jet breaks the sound barrier, except here the air is made of ionized hydrogen, and the explosion spans millions of light years. Every ripple carries energy equivalent to billions of supernovae, and as they overlap, the heat builds to extremes unseen anywhere else in the known universe. Using the Chandra X-ray Observatory, scientists mapped the thermal structure of this chaos. The hottest regions appear as bright blue patches in composite images, tracing where the gas is most compressed. Those zones mark the latest impact sites, the places where the subclusters' gas halos collided most recently. Cooler regions, shown in softer shades, represent areas where the shockwaves have already passed and the gas is beginning to settle. Together, these temperature gradients reveal the sequence of collisions that shaped the system, almost like forensic burn marks from multiple explosions. But this temperature isn't the same everywhere. Its heat changes a lot from one part of the cosmic collision zone to another, because it is so big and rough. Some areas of gas are cool enough to make thick filaments, while other areas are still very hot, hundreds of millions of degrees. This uneven heating makes pressure differences that cause turbulence, which are huge spinning plasma waves that can be seen from millions of light years away. Scientists are still trying to figure out how the energy in this cluster is being spread by the magnetic fields inside these eddies, which twist and get stronger. The temperatures also reveal how different forms of matter behave under extreme conditions. The gas, made mostly of hydrogen and helium, slows down and heats up as it collides. The galaxies themselves, however, barely notice. They pass through the chaos almost unaffected because the distances between stars are so enormous that direct collisions are rare. Meanwhile, dark matter, which interacts only through gravity, moves straight through the melee as if nothing happened. This separation, gas lagging behind, galaxies racing ahead, and dark matter gliding silently through, is one of the clearest demonstrations of how these components behave differently under pressure. It's a real-world physics experiment on a cosmic scale. The incredible heat also plays a key role in shaping the cluster's long-term future. At these temperatures, the gas emits X-rays that radiate energy into space. Over billions of years, that radiation will cause the plasma to cool and condense, eventually feeding new waves of star formation within the cluster's galaxies. But right now, the system is far from equilibrium. The ongoing collisions keep reheating the gas faster than it can cool, locking the entire region in a state of perpetual turbulence. Even the cosmic microwave background, the faint afterglow of the Big Bang, feels the influence of this heat. As those ancient photons pass through the hot plasma, some gain energy through a process known as the Sunyaev-Zeldovich effect, leaving subtle imprints in the background radiation that scientists can detect. Those distortions act like fingerprints, confirming both the cluster's temperature and its ongoing motion through space. To study this hot area is to look into the engine room of how the universe has changed over time. It's where the raw power of gravity is turned into heat on unimaginable levels. The cosmic collision zone is a live example of how the universe builds and breaks itself. It is a fire of chaos whose heat shows us the physics that control the universe. The shock fronts. There are scars from every big impact in the universe. In the cosmic impact zone, those scars are huge shock fronts that move through space like shock waves from an explosion. They mark the edges where clouds of gas moving at thousands of kilometers per second crash into each other and push the plasma to its extremes of temperature and density. In visible light, these lines can't be seen, but in X-rays and radio waves, they're clear as day, appearing as bright arcs that show where a cosmic disaster is happening. Scientists see more than just beauty in these fronts. They are strong signs that show how energy moves and breaks apart during some of the most dramatic events the world has ever seen. When two clusters collide, their hot intergalactic gases don't merge peacefully. They smash into one another, producing a wall of compression that races outward like a cosmic sonic boom. The physics is similar to what happens when a jet breaks the sound barrier, except here the air is an incredibly thin plasma. Particles of ionized hydrogen and helium spread across millions of light years. As the gas compresses, it emits X-ray radiation, lighting up the collision zone like a celestial explosion frozen in time. These fronts are where kinetic energy, the motion of entire galaxy clusters, is converted into heat, turbulence, and radiation. In the cosmic collision zone, astronomers have identified multiple overlapping shock fronts, each marking a separate impact event in the cluster's chaotic history. Some of these fronts stretch for several million light-years, making them among the largest continuous structures ever observed. Using the Chandra X-ray Observatory, scientists have mapped them in exquisite detail. The brightness of the X-ray emission traces the density of the gas, while temperature gradients reveal the strength of each shock. In some areas, temperatures spike from 20 million to over 100 million kelvins in just a few 100,000 light-years. A violent transition that makes this region one of the most energetic known environments in the observable universe. But there's another layer to these shock fronts, one that can't be seen in X-rays. Radio telescopes such as the Very Large Array, VLA, and LOFAR detect diffuse radio relics, vast arcs of radio emission that trace the paths of high-energy electrons spiraling through magnetic fields. These electrons are accelerated by the shocks to near-light speeds, producing synchrotron radiation, a kind of electromagnetic hum that reveals the invisible architecture of the cluster's magnetic field. When overlaid on X-ray maps, the radio relics align perfectly with the shock fronts, confirming that the collision has created colossal particle accelerators stretching across intergalactic space. It was really fascinating to find out that these fronts don't just heat the gas, they also move it. Behind every shock is a wake of turbulence, where plasma eddies move back and forth like waves in the ocean. These rough areas make magnetic fields stronger and heat move around, making complicated patterns of motion that last for hundreds of millions of years. Scientists can see plasma physics on a scale that can't be made in a lab when they study these interactions. It helps us understand how galaxies lose their gas, how intergalactic magnetic fields change over time, and how cosmic rays, the very high-energy particles that hit Earth all the time, might speed up as they move through the universe. Picture 4 huge weather systems crashing into each other slowly. Where the fronts meet, they make huge walls of pressure. After they leave, shock waves move behind them and cause storms of heat and radiation. It is called the cosmic collision zone, and it is made up of plasma blasts that are millions of light years across. If you look at that storm through Hubble, Chandra, or ALMA, you will see a different part of it each time. In visible light, it looks calm, with galaxies spread out over a dark space like glitter. As you look deeper into X-rays or radio waves, however, the calm turns into chaos. You can see arcs, filaments, and knots of matter crashing into each other and then bouncing back like waves in a cosmic sea. These shock fronts are more than relics of destruction. They're the engines that drive evolution within the cluster. They strip gas from galaxies, quench star formation, and shape the future of the entire system. Over billions of years, the energy they release will fade, the gas will cool, and the fronts will settle into a smooth halo of hot plasma, the mark of a mature, stable galaxy cluster. But for now, the region is still alive with motion. Every shock is a ripple in time, a reminder that the universe builds its greatest structures through violence and instability. What's even more noteworthy is how the shocks change gravity lensing. The way light bends around a gas changes based on how dense it is. This means that the shock fronts can be seen in radiation and can also be measured in terms of distortion. Scientists use these changes to figure out how mass is spread out in the impact zone. This links the physics of plasma to the geometry of space-time. Turbulent magnetic fields. The magnetic fields of the cosmic collision zone are like the scars that the shock fronts leave behind. They are powerful and can't be seen. They move through the superheated plasma of the cluster, controlling the movement of charged particles and changing how energy moves across millions of light years. This area is unique because its magnetic fields are not just theories. They can be seen. This is one of the few times in science that something so mysterious can be seen by looking at how it affects light. When astronomers first studied the collision zone with the Very Large Array, VLA, and later LOFAR and ALMA, they detected faint, ghostly radio emissions forming broad halos and filaments around the cluster. These signals were synchrotron radiation, the electromagnetic glow produced when high-speed electrons spiral through magnetic fields at nearly the speed of light. The shape and polarization of this radiation revealed that the region was threaded by complex, tangled magnetic structures, twisted and stretched by the violent motion of colliding clusters. Unlike the steady, ordered fields seen in calm galaxies, these were chaotic, dynamic, and constantly reshaping themselves under the pressure of turbulence. The origins of these fields go back billions of years. The universe likely began with tiny seed magnetic fields, faint traces left over from the early plasma after the Big Bang. Over cosmic time, events like supernova explosions, galactic winds, and, most dramatically, cluster mergers amplified them. In the cosmic collision zone, this amplification is on full display. As the subclusters smash together, their moving plasma generates electric currents. Those currents, through a process called the dynamo effect, strengthen existing magnetic fields and twist them into larger and more complex patterns. The result is a colossal magnetic web that covers millions of light years, influencing everything from the motion of hot gas to the propagation of cosmic rays. In X-ray images from Chandra, the regions of strongest turbulence, where temperatures fluctuate rapidly, align closely with areas of intense radio emission. This alignment tells scientists that magnetic energy and thermal energy are deeply intertwined. The shocks that heat the gas also compress and stretch the magnetic fields, making them stronger in localized patches. These enhanced fields act like invisible fences, trapping charged particles and forcing them to spiral instead of flying straight through space. As those particles spiral, they emit the very radio waves that allow us to see the magnetism at work. The strength of the magnetic fields here is astonishing, often measured at several microgauss, comparable to those within spiral galaxies like the Milky Way, but spread across regions far larger. In some places, scientists have detected evidence that the field strength varies sharply, suggesting that entire filaments of plasma are being folded and twisted by the merging subclusters. These folds create layers of alternating magnetic polarity, similar to what happens inside a turbulent ocean where currents meet. The energy stored in these tangled fields can rival that of the thermal plasma itself, showing that magnetism is not a side effect of the collision, but a major player in its physics. This magnetized turbulence has profound consequences. It governs how quickly the cluster's gas cools, how particles are accelerated, and how radiation travels through space. It may even influence how stars form within the surviving galaxies. In less extreme environments, magnetic fields help stabilize galactic disks and guide cosmic rays out into intergalactic space. Here, they're constantly being ripped apart and reassembled, turning the collision zone into a living experiment on how the universe manages energy at its largest scales. Scientists can see how magnetism might affect the cosmic web, which is the huge network of filaments and gaps that make up the structure of the universe on a big scale. This is one of the most interesting things about the cosmic collision zone. If mergers like this one can boost weak primordial fields to the levels of strength seen today, then crashes between clusters could be what made the universe magnetic. The magnetic remnants we see today could be the building blocks of the universe's unseen structure. It is very hard to study signs that are so weak. Astronomers use long exposures and the way radio waves are polarized to figure out the field's direction and strength. A method called Faraday rotation can show us how the magnetic lines are lined up along our line of sight, with just a small change in orientation. Researchers can figure out the three-dimensional structure of the magnetic plasma by putting together hundreds of observations made at different wavelengths. The dark matter map. Scientists took away all the layers they could see of the cosmic collision zone, including the stars, the gas, and the radiation. What was left was a puzzle that not even light could answer. Everything was shaped by something huge that could not be seen with any lens. Dark matter, which made up most of the cluster's mass, was that something. Astrophysicists were able to map it for the first time, but not by seeing it. Instead, they watched how it bent the light from the galaxies behind it. The cosmic collision zone became one of the best natural laboratories in the universe for studying dark matter because of its incredible complexity. When four massive clusters collide, their dark matter halos, vast invisible cocoons that surround each cluster, don't behave like gas or stars. They pass through each other almost without resistance, interacting only through gravity. Meanwhile, the clouds of hot gas slow down and collide, creating X-ray bright shock fronts. This separation between the visible gas and the invisible mass gives scientists a way to trace dark matter's position and movement. Using gravitational lensing, astronomers from NASA, ESA, and multiple research teams mapped how the light of background galaxies warped as it passed through the region. The distortions formed a pattern, subtle but unmistakable, showing that most of the cluster's mass wasn't where the glowing gas was. Instead, it was offset, drifting alongside the galaxies rather than the plasma. This was a crucial finding. It confirmed that dark matter behaves differently from normal matter, passing cleanly through collisions that would stop ordinary particles dead in their tracks. To create these maps, scientists combined data from Hubble, Chandra, and ground-based observatories like Subaru in Hawaii. Hubble's sharp images revealed the gravitational arcs, elongated streaks of light from distant galaxies that outlined the cluster's gravitational field. Chandra's X-ray data pinpointed the hot gas, while the optical data tracked where the galaxies themselves were concentrated. When all three layers were compared, the differences jumped out. The densest regions of dark matter, inferred from lensing, didn't align with the brightest X-ray peaks. That mismatch is the visual proof of dark matter's ghostly passage through chaos. This kind of displacement had only been seen clearly once before, in the Bullet cluster, a smaller but famous collision between two galaxy clusters. There, too, the dark matter had separated from the gas, offering some of the strongest evidence for its existence. But the cosmic collision zone took that story to another level. Its four-way merger provided not one but multiple overlapping examples of dark matter behaving independently of visible matter. The complexity of its structure meant scientists could study dark matter under a variety of conditions, different velocities, angles, and collision stages, all within one enormous cosmic system. Researchers turned this region into a living experiment in gravitational physics. They created mass density models to estimate how dark matter was distributed, calculating its total mass at roughly 10 to the 15th solar masses, a quadrillion times the mass of the Sun. That makes it one of the most massive structures ever measured. But it wasn't just the quantity that fascinated scientists. It was the way it moved. Computer simulations showed that the dark matter halos didn't simply overlap and merge. They oscillated around one another, creating ripples in the cluster's gravitational potential. These oscillations could subtly alter the paths of light from galaxies behind them, a phenomenon that researchers now use to test theories of how dark matter interacts with itself. When groups come together, one of the main concerns is whether dark matter can crash or spread out just a little. No clear lines between gas and dark matter might show up if it did. Instead, mass peaks might become more even. These peaks are still clearly visible in the cosmic collision zone. This suggests that dark matter either doesn't interact with anything at all, or does so much less often than normal matter. This discovery helps us figure out what dark matter might be. It could be weakly interacting particles, WIMPs, or something even stranger, like axions or sterile neutrinos. The gravitational lensing maps also turned this chaotic region into a cosmic magnifying glass. The distorted light from galaxies lying far behind the cluster was amplified, allowing astronomers to study galaxies that formed just a few 100 million years after the Big Bang. In this way, dark matter, despite being invisible, became an instrument of discovery, bending light so powerfully that it revealed the earliest structures in the universe. The role of dark energy. Gravity is pulling hard on the cosmic collision zone, but dark energy is also pulling against it in a more mysterious way. This unseen force determines not only the future of this cluster, but also the future of the whole universe. Near the surface, the impact zone looks like a place where gravity rules. 4 groups of gigantic objects are pulled together by their own weight, and they have been fighting for billions of years. But if you back up, the picture changes. There is more and more room between them and all other worlds. The very fabric of the world is growing, and it's expanding faster. Dark energy is what makes it happen, and you can feel its quiet impact even in this area of terrible violence. To see how dark energy and gravity interact here, scientists had to look beyond the visible chaos. They measured how fast the entire cluster system is moving relative to the expanding universe around it. Each of the 4 subclusters is massive enough to warp space-time, but even combined, their gravitational pull is minuscule compared to the expansion acting across billions of light years. By studying how galaxies within the cluster move, how fast they orbit, how their light shifts due to motion, astronomers can tell how tightly gravity is holding them together. When compared to distant younger clusters, something subtle emerges. Over time, clusters like this one become less dense, their outer galaxies drifting away faster than gravity can pull them back. That slow unraveling is the fingerprint of dark energy. It's not tearing the cluster apart directly, but it's stretching the space around it, reducing the chances that distant clusters will ever merge again. In a universe without dark energy, systems like the cosmic collision zone would continue to grow indefinitely, swallowing smaller clusters until vast superstructures spanned hundreds of millions of light years. But dark energy changes the rules. It pushes everything apart faster than gravity can gather it. In effect, the age of major cluster formation is ending, and regions like this are becoming the last great mergers before the universe's expansion isolates them forever. To quantify this invisible pressure, astronomers use the cosmic distance ladder, a set of methods involving supernovae, the cosmic microwave background, and galaxy surveys that trace how expansion changes over time. Observations show that dark energy accounts for roughly 70% of the universe's total energy content, with dark matter making up about 25% and ordinary matter less than 5%. That imbalance means that even the most massive collisions, like the one unfolding here, are ultimately small ripples on an ocean controlled by dark energy's outward thrust. But how does this affect the cosmic collision zone itself? Over billions of years, as dark energy stretches space, the gravitational ties between its outer galaxies will weaken. The central mass, a future supercluster formed from the merger of the four cores, will remain bound, its gravity strong enough to resist expansion locally. However, beyond its outer boundary, galaxies and gas will drift away, leaving the supercluster isolated in an expanding void. It will shine for eons, then gradually fade as its stars burn out and no new material falls in to replace them. Dark energy ensures that isolation is permanent. To better understand this process, scientists compare observations of clusters at different epochs of cosmic history. Younger clusters, seen in the more distant universe, are denser and more compact. Older ones, like the cosmic collision zone at roughly 5.5 billion light-years away, already show signs of expansion and internal motion shaped by dark energy's influence. By measuring the temperature and density of the gas, the speed of member galaxies, and the gravitational potential inferred from lensing, astronomers can build models predicting how the cluster will evolve in a universe dominated by accelerated expansion. Based on these models, there won't be any more large-scale impacts for tens of billions of years. There will be no more joining clusters or galaxies falling into them, and the cosmic web will start to break up. The cosmic collision zone, which used to be a stage of unthinkable violence, will become quiet, with darkness growing all around it. Its light will keep moving through space, but fewer and fewer people will be able to see it. In a very far future, dark energy will have stretched the universe so much that galaxies far away will no longer be visible, and no one will ever be able to see their light. Gravitational lensing power. Not only is the cosmic collision zone a place where things are destroyed, but nature also made it into a telescope. Because it has so much mass, it bends space-time itself, making it one of the strongest gravity lenses that has ever been seen. It's not possible for light from galaxies far behind the cluster to move in straight lines. Instead, it bends around the gravity of the cluster, making long loops, stretched reflections, and even more than one picture of the same faraway galaxy showing up in different sky locations. Astronomers can see farther into the universe with this natural zoom than with any lens made by humans alone. The power of this effect comes from pure mass. The four merging subclusters of the cosmic collision zone contain over 1 quadrillion solar masses of material, dark matter, gas, and stars all combined. That mass acts like a cosmic magnifying glass, bending the light of objects billions of light years behind it. When the Hubble Space Telescope first imaged the area in detail, the view was astonishing. Faint, ghost-like arcs looped around the central region, some so thin and perfectly curved that scientists knew they were seeing entire galaxies from the early universe, stretched by the gravity of the collision itself. Each arc tells a story about both the background galaxy and the lensing cluster. By measuring how much the light bends, researchers can calculate how the cluster's mass is distributed, including the invisible dark matter. The greater the curvature, the denser that part of the cluster must be. In this way, gravitational lensing acts as both microscope and map. It magnifies distant galaxies while simultaneously tracing the unseen structure of the lens doing the bending. In the cosmic collision zone, where mass is scattered across 4 interacting cores, that map becomes a complex tapestry of overlapping gravitational wells, each distorting space in its own direction. To make sense of it, astronomers divide lensing into 2 types. Strong lensing occurs near the cluster's core, where gravity is most intense. There, light from background galaxies is stretched into visible arcs or rings, known as Einstein rings. These features are so precise that they can be modeled mathematically, allowing researchers to reconstruct the original shapes and positions of the background galaxies. Weak lensing, on the other hand, happens farther out, where the distortions are too subtle to see individually. Instead, scientists analyze the average shapes of thousands of faint background galaxies to reveal a collective pattern of stretching. Combining both methods creates a detailed 3D map of mass, visible and invisible, throughout the entire cluster. The cosmic collision zone was chosen as one of the key targets in the Frontier Fields program, a collaboration between NASA, ESA, and the Space Telescope Science Institute. By pairing Hubble's visible and infrared imaging with gravitational lensing, astronomers were able to peer more than 13 billion light-years into the past. The result was one of the deepest looks into the early universe ever achieved. Dozens of galaxies previously invisible to any telescope appeared, some dating back to only a few 100 million years after the Big Bang. The cluster's chaotic gravity, born of destruction, became an instrument of discovery. Most gravity lenses are made by a single cluster that is pretty steady, but in this case, the four-way merger changes the gravity environment all the time. The orientation of the mass changes slightly as the subclusters move, which changes how the background light bends. This makes a dynamic lens, which changes over time. This gives scientists a unique chance to study how lensing works in a merged, unstable world. Researchers can see how gravity changes by following these changes over many years of Hubble data. Hubble's deepest view through the chaos. Scientists didn't just see a bunch of galaxies when they looked through the Hubble Space Telescope at the cosmic collision zone. Even though this cluster's gravity is very strong, it bends light from galaxies far away like a magnifying glass. Because of this, NASA picked this area for its Big Frontier Fields program. This program uses Hubble's visible and infrared eyes, along with gravitational lensing, to look further into the universe than ever before. Hundreds of weak and fragile galaxies that shine from when the universe was less than 1 billion years old were found behind the chaos. This shocked scientists. Through the collision's warped gravitational field, Hubble could amplify the light from those remote galaxies by factors of 10 to 100 times. That's how astronomers managed to detect galaxies that would otherwise be invisible. So dim, they could never be observed directly, even by the most powerful space telescopes. In the resulting images, the cosmic collision zone looks almost like a shattered mirror. The bright cores of galaxies in the foreground, surrounded by streaks, arcs, and ghostly smudges. The reflected echoes of distant light. Each distortion represents a galaxy from the dawn of cosmic history, magnified through the wreckage of colliding clusters. This cosmic trick allowed scientists to turn disaster into discovery. The massive violence of the collision, the shock fronts, the turbulent magnetic fields, the dark matter cores, all serve a higher purpose as a natural telescope. Hubble's data showed distant galaxies forming stars at extraordinary rates, far faster than expected for such an early epoch. Some of these galaxies appeared only a few 100 million years after the Big Bang, when the first heavy elements were just beginning to form. They're small, irregular, and chaotic, much like the cluster that revealed them, but they hold the secrets of how the first generations of stars lit up the cosmos. The Frontier Fields campaign, which observed 6 massive galaxy clusters, including this one, produced some of the deepest images in astronomical history. By layering Hubble's optical data with infrared imaging from Spitzer and X-ray data from Chandra, astronomers built a multi-dimensional view of both the cluster and the galaxies it magnified. Each wavelength added a new layer of information. Hubble revealed the structure and color of galaxies. Spitzer showed the heat signatures of star formation. Chandra traced the hot gas between the colliding clusters. Together, they created a window into two cosmic stories at once: the ongoing merger in the foreground and the birth of the earliest galaxies in the background. The finding that galaxies make stars hundreds of times faster than the Milky Way was one of the most surprising finds. It took only a few thousand light years for these young systems to use up all of their gas to make new suns in bright bursts. Without gravity lensing, they would have stayed hidden forever because they were too far away and faint for any camera to see. But the cosmic collision zones' skewed gravity turned them into bright, stretched smears of light on Hubble's cameras. These were the universe's first star cities, made bigger by one of its worst disasters. In some cases, astronomers spotted multiple images of the same galaxy, each appearing in a different place because the light had taken slightly different paths through the warped spacetime of the cluster. By measuring the time delay between these images, researchers could calculate how much mass, including dark matter, was causing the bending. These time delays even help refine estimates of the Hubble constant, the rate of cosmic expansion, linking the smallest observable distortions to the largest scale motion of the universe itself. X-ray glow of violence. Hubble's pictures showed how beautiful the cosmic collision zone was, but Chandra's X-ray pictures showed how dangerous it was. Gravitational lensing creates beautiful arcs, but below them is a hellish blaze of gas and plasma. It's so hot that it can strip atoms of their electrons and turn matter into a fully charged state. When Chandra first looked at this area, the data showed something that no optical camera could ever show: X-ray emitting clouds of very hot gas that stretched across millions of light years. They looked like the remains of a cosmic explosion. This glow is not random. It outlines the collision's anatomy, the regions where the four subclusters smashed together, and the violence is at its peak. Each X-ray filament traces the shock fronts rippling through the cluster's plasma, marking where motion and energy collide. The patterns resemble firestorms seen from orbit after volcanic eruptions, except here the eruption is gravitational. The gases from separate clusters have rammed into each other, compressing and heating to unimaginable temperatures. The result is a kind of intergalactic furnace, radiating so powerfully that it outshines thousands of galaxies combined. At these temperatures, normal matter behaves more like liquid fire than gas. Protons and electrons move so fast that collisions between them emit Bremsstrahlung radiation, braking radiation, the source of the X-rays Chandra detects. The brightness of this emission tells astronomers how dense and hot the plasma is in different regions, letting them reconstruct the collision's full 3D structure. When the data were converted into color images, the result looked almost like an artist's rendering: streaks of electric blue and white against a black cosmic backdrop. Except every pixel represented real, measurable energy released by billions of tons of matter slamming together. The X-rays also show something extraordinary about how energy is distributed. Instead of being confined to one central point, the glow extends over millions of light years, a sign that the entire cluster is still violently mixing. The outer filaments, stretching like wings from the core, are evidence that gas from the subclusters has not yet settled. The collisions are ongoing. Some regions show sudden jumps in temperature, clear indicators of shock fronts, while others are cooler, suggesting older impacts now dissipating. This temperature layering gives scientists a timeline of the event, almost like tree rings marking the stages of a cosmic war. When a cluster is steady, hot gas tends to gather in the middle, making a smooth, uniform halo. The fact that the plasma is torn and skewed here shows that the gravity balance has been broken. The galaxies are spread out, and some have lost all of their gas due to the pressure of the plasma around them. This is known as ram pressure stripping. Once normal galaxies are now nothing but skeletons because of the impact. The X-ray hot winds have blown away the material that used to make stars. Chandra's observations also exposed the relationship between visible and invisible matter. When compared to Hubble's lensing maps, the X-ray peaks, where the gas is densest, don't line up with the gravitational mass peaks, which trace dark matter. This mismatch tells scientists that dark matter isn't colliding or slowing down with the gas, it simply passes through. It's one of the clearest pieces of evidence that dark matter is collisionless and interacts only through gravity. The cosmic collision zone is thus not just a display of energy. It's a cosmic laboratory where the boundaries between matter types can be observed in real time. This X-ray glow can be seen in the cosmic microwave background, which is the background energy of the universe. Some of those old photons gain energy as they pass through the hot plasma. This is called the Sunyaev-Zeldovich effect, and it lets scientists measure the cluster's pressure and motion in ways that light alone couldn't. When you put together X-ray and microwave data, they show huge forces at work, shock fronts racing through plasma, turbulence increasing magnetic fields, and heat leaking into space. Radio relics and halos. Radio telescopes, not optical or X-ray eyes, show a completely different world in the cosmic collision zone. This world is made up of waves that can't be seen and charged particles speeding through magnetic storms. It doesn't just glow, the cluster hums. Radio relics and radio halos are weak, diffuse signals made when the collision's shock waves speed up electrons to almost the speed of light. They can be heard over millions of light years. These ghostly buildings are some of the biggest radio-emitting objects that have ever been seen in the universe. Radio relics are the fossils of the collision itself. They form along the edges of the cluster, tracing the shock fronts that Chandra saw in X-rays. As gas clouds slammed together, immense compression waves swept through the plasma, accelerating particles and amplifying magnetic fields. Those accelerated electrons spiral along the field lines at relativistic speeds, producing synchrotron radiation, a faint, steady glow that radio telescopes can detect. In the cosmic collision zone, these relics appear as long, curved filaments, stretching for millions of light years, marking the boundaries of ancient cosmic impacts. The most famous of them is a massive arc, a diffuse ribbon of radio light that wraps around part of the cluster's outskirts like a scar. Further in, the cluster hosts an even more mysterious structure, the radio halo. Unlike relics, which trace well-defined shock edges, halos fill the central region with a diffuse, cloud-like radio emission. These halos are rare, and their existence tells scientists that the turbulence in this cluster is extreme. The chaotic motion from multiple merging subclusters stirs the plasma so violently that electrons are constantly re-energized. This perpetual motion sustains the halo's glow across tens of millions of years. Essentially, the entire heart of the cluster has become a vast particle accelerator, with every magnetic ripple acting like a cosmic turbine. To reveal these features, astronomers used the Very Large Array, VLA, in New Mexico and later LOFAR, the Low Frequency Array in Europe, which excels at detecting the long, low-energy radio waves emitted by ancient electrons. What they found confirmed that the cosmic collision zone is one of the most radioluminous merging clusters ever discovered. The relics outline the outer shock fronts, while the central halo fills the inner space between the four subclusters, overlapping perfectly with the regions of high-temperature plasma seen in X-rays. Each wavelength tells part of the story. X-rays show the heat of impact, radio waves trace the energy released by magnetic chaos, and optical images mark the galaxies caught in between. How magnetic chaos and particle acceleration work together was one of the most important things learned in this area. The artifacts show highly polarized light, which means that the radio waves move in certain directions. This shows how the magnetic fields were structured in the impact zone. Scientists use the direction of this polarization to figure out how shocks line and stretch the fields. On the other hand, the halo radiation is mostly unpolarized, which means that the fields are random and jumbled because of the fast motion. Astronomers can make a picture of how order turns into chaos on a size that is much bigger than any human experiment. The electrons producing these radio waves can reach energies up to 10 trillion electron volts, but they don't stay that way for long. They lose energy quickly, fading over tens of millions of years. This means the radio relics and halos are fleeting. They exist only while the merger remains active. Once the shocks subside and the turbulence dies, the glow fades into silence. That impermanence is what makes these features so valuable. They capture the collision in motion, not as a fossil. They are snapshots of cosmic energy transfer happening right now. The mystery of energy dissipation. It's strange that the cosmic collision zone is a place where energy can't be stopped, but is still steady. When four huge groups of galaxies crash into each other, shock waves are sent out over millions of light years, and gas is heated to 100 million kelvins. But the system doesn't explode or fall apart. It shines. It will last. The mysterious thing is how that energy, the physical rage of the merger, is lost. Where does it go? How does it change into the light, heat, and radio waves that antennas can pick up without breaking up the cluster? On Earth, energy dissipation is simple to observe. When a hammer strikes a nail, its kinetic energy becomes heat and sound. But in space, there's no air, no friction, and almost no matter to absorb energy. In the cosmic collision zone, most of the volume is vacuum, a few atoms per cubic meter. Yet this emptiness carries some of the hottest plasma in the universe, proof that enormous amounts of energy have somehow been transferred and distributed efficiently. Understanding how that happens is one of the great challenges of astrophysics. When two galaxy clusters collide, most of their visible matter, the hot gas between galaxies, crashes together. This interaction produces shock fronts, which convert a fraction of the cluster's bulk motion into heat. But only a small part of the kinetic energy shows up as temperature. The rest disappears into turbulence, waves, and magnetic fields. Astronomers call this the energy budget problem, the difficulty of accounting for where all that motion goes. The cosmic collision zone, with its complex geometry and multiple impacts, is the ideal laboratory to study it. High-resolution X-ray maps from Chandra show evidence of turbulent mixing throughout the cluster's plasma. Gas in some regions moves at thousands of kilometers per second, creating shear flows and eddies. These turbulent motions cascade energy down to smaller scales, much like a storm system on Earth. Eventually, microscopic collisions between charged particles convert that motion into heat, a process known as viscous dissipation. It's slow, subtle, and invisible, but over hundreds of millions of years, it converts bulk kinetic energy into thermal energy, maintaining the plasma's blistering temperatures long after the initial collision. Observations from radio telescopes revealed that the cluster also contains enormous populations of relativistic particles. Electrons accelerated almost to the speed of light. Those particles emit the synchrotron radiation seen in the cluster's radio relics and halos, meaning part of the collision's energy must go into accelerating them. How that happens remains an open question. Some researchers point to diffusive shock acceleration, a process where particles repeatedly bounce across magnetic shock fronts, gaining a little energy with each crossing until they reach relativistic speeds. Others suggest that turbulence itself re-energizes electrons through random magnetic interactions, keeping the radio halo glowing long after the shocks fade. Then there's the role of magnetic reconnection, a phenomenon where twisted magnetic field lines snap and realign, releasing energy in explosive bursts. It's similar to what powers solar flares on the sun, but on a scale trillions of times larger. In the cosmic collision zone, tangled magnetic fields created by the merger could reconnect constantly, converting magnetic tension into heat and particle acceleration. Each of these processes, shocks, turbulence, reconnection, consumes a share of the cluster's energy, but exactly how much each contributes is still unknown. The heat that does emerge doesn't radiate away quickly. The plasma is so diffuse that its cooling time, the period needed to lose its energy through radiation, exceeds the current age of the universe. That's why the collision zone still glows so intensely today, even though the initial impacts began billions of years ago. The energy isn't lost, It's simply redistributed, locked in a cycle of heating, mixing, and slow decay. In that sense, the cluster is less an explosion and more a slow-burning engine, one that will keep shining for eons. Scientists use computer models to test these ideas. Supercomputers make models of how plasma moves, how magnetic fields behave, and how particles speed up in an environment that is similar to the cluster. The findings show that even though turbulence does a good job of spreading energy, only a small amount gets to the dense centers of the joining groups. Most of it stays stuck on the edges, where there isn't much gas and strong magnetic fields. That's why radio relics, which are leftovers from particle acceleration, show up on the sides, and X-rays shine through the middle. 4 cores, 4 histories. In the cosmic collision zone, 4 groups of galaxies are crashing into each other, but not all at once. Instead, they have been crashing into each other over and over for hundreds of millions of years. Each core has its own story, mass, and motion. When they come together, they make the messiest and most complicated merger that has ever been seen. Astronomers mapped this area using different wavelengths and found not one center, but 4. Each center was glowing in X-rays and leaving behind lines of shocked gas, dark matter, and galaxies that had been messed up. You have to look at each part of the system to understand the whole. The collision is not a single event, but 4 lives coming together in the same place. The first core, the dominant central cluster, is the heavyweight of the system. It contains the bulk of the total mass and serves as the gravitational anchor for the entire merger. Chandra's X-ray images reveal a massive elongated cloud of superheated plasma surrounding it, evidence of older collisions that have already partly settled. This central core likely existed before the others arrived, acting as the gravitational well that drew them all in. Its galaxies are densely packed, its dark matter halo immense, and its temperature profile smoother than the rest, a sign that it's already in the late stages of merging smaller fragments into itself. The second core, often called the bullet-like subcluster, is smaller but faster. It's currently moving through the system at more than 3,000 kilometers per second, carving a bow shock through the intergalactic gas. This high-speed core has left a distinct trail of turbulence and stripped plasma in its wake, like a cosmic comet. Its dark matter has surged ahead of its gas, proving once again that dark matter interacts only through gravity, while ordinary matter crashes and slows. Chandra and Hubble data show a clear displacement between this core's X-ray peak and its lensing mass peak, a visual separation between matter types. It's one of the cleanest demonstrations in the known universe of how dark matter and baryonic matter part ways during collisions. The third core, a fragmented remnant cluster, is in shambles. It shows little coherence in either X-ray or optical light, suggesting that tidal forces and prior impacts have already torn it apart. What remains is a scattering of galaxies and plasma filaments, moving erratically under the influence of the larger core's gravity. This fragment may once have been a massive cluster on its own, but repeated encounters have stripped it of its gas and flattened its dark matter halo. In a few billion years, it will likely disappear entirely into the gravitational center of the merged supercluster, its identity erased. The fourth core, the incoming subcluster, is the most enigmatic. It appears to be approaching from the outer regions of the system, plunging into the collision zone for the first time. Its gas and galaxies are still relatively intact, and its temperature is lower than the surrounding plasma, meaning it hasn't yet absorbed the full impact of the merger. Observations suggest it's falling along a filament of the larger cosmic web, drawn toward the central cluster by gravity. In a few 100 million years, it will crash through the system's heart, creating new shock fronts and reheating the plasma all over again. The cosmic collision zone, in that sense, is not a single event frozen in time. It's an evolving sequence of impacts, each reigniting the furnace as new material falls in. When astronomers overlay the positions and velocities of these 4 cores, a pattern emerges, a multi-directional convergence unlike anything seen elsewhere. Instead of 2 clusters meeting head-on, This system involves 4 gravitational centers, pulling, twisting, and distorting each other's orbits. The result is a sprawling web of energy, a gravitational storm where galaxies are scattered, gas is shredded, and magnetic fields are continuously rebuilt. Each core contributes a unique set of shock waves, temperatures, and velocities, creating the layered complexity that makes this cluster so scientifically valuable. The light that comes from these cores also tells different stories. It's likely that the squeezing of gas during impacts is what sets off strong star formation in some of their galaxies. Others are dormant, having been stripped of all their matter and left to float through the plasma like starless husks. All of them together show every stage of the development of the galaxy squished into one venue. The mix of young galaxies that are bursting with stars and old spiral galaxies that are dying is like a time capsule that shows how collisions change whole groups of stars. The fastest moving cluster core ever seen. The cosmic collision zone is made up of 4 titans that are joining. One giant stands out because of how fast it is moving. It is a subcluster core that has gotten out of control. It is a dense mass of galaxies and dark matter moving through the system at over 3,000 kilometers per second, which is almost 1% of the speed of light. That's really hot in cosmic terms. It's the fastest moving cluster core that has ever been seen, and the way it moves through the plasma around it is changing what scientists thought was possible for galaxy clusters that are held together by gravity. This subcluster, often described as the bullet of the system, is a living demonstration of momentum on an astronomical scale. When 2 clusters collide, gravity accelerates them toward each other, but this one appears to have been catapulted beyond expectations. Its speed suggests not just a head-on impact, but a complex gravitational interaction, possibly a slingshot effect involving multiple subclusters. In this scenario, one core passes close to another, gaining velocity as gravitational forces exchange energy. What's left behind is a trail of devastation visible across wavelengths, gas stripped away, shock waves rippling outward, and magnetic turbulence cascading for millions of light years. The Chandra X-ray Observatory first detected the bullet's path through the cluster's hot plasma. In the images, the front of the subcluster forms a bright, sharp arc, a bow shock where intergalactic gas is compressed and heated as the core plows through. Behind it, a long wake of cooler, less dense gas trails away, marking where the cluster's atmosphere has been peeled off by the force of its own motion. This bow shock is remarkably similar to that of the famous bullet cluster, the smaller 2-body merger often used as evidence for dark matter. But here, the effect is magnified by the scale and complexity of a 4-way collision. What's truly amazing is that this bullet keeps going fast, even though the plasma it's going through is pulling it down. The subcluster would slow down quickly if the hot gas was dense enough. It just keeps going, which is a sign that most of its mass is in dark matter, which mostly skips through the other stuff around it. This is the reason why the dark matter peak comes before the gas in maps that show both gravity lensing and X-ray emission. The plasma peak comes after the dark matter peak. The galaxies inside the bullet follow the path of the dark matter and glide through the storm with little trouble. However, the gas is severely compressed and heated. This clean separation is invaluable to physicists. It shows that dark matter does not collide, radiate, or lose energy the way normal matter does. It behaves like a ghost, gravitationally influential, but otherwise untouchable. The bullet's motion provides one of the clearest natural experiments for studying these differences. By modeling its trajectory and comparing the positions of dark matter and gas, scientists can test whether dark matter interacts even slightly with itself. So far, the results suggest it doesn't. The sharpness of the bow shock and the lack of slowdown indicate that dark matter remains effectively collisionless, passing through both gas and other dark matter halos without friction. The bullet's passage also reveals the enormous energy hidden in the collision zone. As it tears through the plasma, it generates shock waves stretching millions of light years, some of the largest in the observable universe. These shocks are visible in both X-ray and radio wavelengths, where they accelerate particles to near-light speeds and amplify magnetic fields. The resulting radio relics trace its path like contrails behind a supersonic jet, marking where the energy of motion is converted into radiation. Astronomers estimate that this single-cause kinetic energy rivals 10 to the 64th ergs, equivalent to the total energy output of billions of supernovae. Yet despite that unimaginable force, the core remains intact, its galaxies gravitationally bound within their shared dark matter halo. The reason lies in scale. The distances between stars are so vast that even when galaxies collide, they rarely touch. The cluster's galaxies, therefore, pass through each other like ghosts, while the surrounding plasma does the real fighting. Tracking the bullet's position over time has given scientists a kind of cosmic stopwatch. By measuring how far it's traveled since the initial collision and comparing that distance to its estimated velocity, researchers can calculate when the impact occurred, roughly 500 million years ago. In cosmic terms, that's recent. The cluster is still recovering, its shock waves still propagating outward, its plasma still settling from the blow. Evidence of cosmic shear. As the cosmic collision zone continues to evolve, its gravity doesn't just bend light, it stretches and twists the very geometry of space. This subtle warping, known as cosmic shear, is one of the most delicate and revealing effects ever detected in astrophysics. It's the fingerprint of gravitational chaos, left not by a single object, but by the collective pull of billions of solar masses moving in violent, asymmetric motion. In this region, where four subclusters collide and dark matter swirls in turbulent patterns, cosmic shear acts like a distortion field stamped across the universe. To the naked eye, the cluster might appear static, but in truth, every beam of light passing through it is bent differently depending on where it travels. This happens because the distribution of mass here is anything but uniform. Some areas are packed with galaxies and dark matter. Others are vast voids of thin plasma. These irregular densities create a gravitational gradient, regions of stronger and weaker pull, that stretches background galaxies into faint, elongated shapes. Detecting that subtle distortion is how astronomers measure cosmic shear. It's not about what's visible, but how visible things change shape when seen through the gravitational haze of a cluster like this one. Using data from the Hubble Space Telescope and ground-based observatories like Subaru in Hawaii, researchers have mapped these distortions across the entire field of the cosmic collision zone. The results are astonishing. Light from thousands of background galaxies shows coherent stretching patterns that trace the underlying dark matter. The directions of elongation point toward the cluster's center of mass, but in this case, there isn't just one. There are multiple centers, each corresponding to a different subcluster. These shear patterns overlap and interfere, creating a twisted mosaic of space-time deformation. It's one of the most complex shear maps ever produced. The complexity of this number is what makes it extremely difficult. The average change in the shape of a background star is less than 1%, which means that even the most sensitive equipment can't see it. Astronomers have to look at thousands of galaxies and take the average of how they are pointing statistically to find it. That's when the pattern starts to show up, weak proof that space has been stretched. Because of the system's huge mass and jumbled structure, that weak signal gets stronger in the cosmic collision zone. Each subcluster adds its own shear mark, and when they come together, they make a gravity lens that is always moving and changing shape as the merger goes on. This phenomenon doesn't just produce beautiful images, it encodes information about the cluster's internal physics. By comparing the shear field to the X-ray and radio maps, scientists can see how dark matter, gas, and galaxies interact, or more accurately, how they don't. The gas, slowed and heated by collisions, lags behind, while dark matter races ahead. The shear pattern follows the dark matter's path, not the gas, confirming once again that most of the cluster's gravity comes from unseen mass. In some regions, the shear even suggests secondary dark matter halos, detached from their original clusters, drifting independently through the plasma. It's like watching gravity's wake, ripples left behind as massive objects tear through space-time. The precision of these measurements has made the cosmic collision zone a cornerstone for testing general relativity on large scales. Einstein's theory predicts exactly how mass should bend and stretch light, and so far, observations here match his equations perfectly. Yet the extreme complexity of this system pushes the theory to its limits. With 4 merging clusters and asymmetric motion in all directions, even small deviations could reveal hints of new physics, perhaps signs of modified gravity or interactions within dark matter itself. For now, the consistency between the data and Einstein's predictions remains a triumph, confirming that general relativity holds strong even in the universe's most chaotic environments. Comparing to the bullet cluster. For many years, the bullet cluster was the best example of a cosmic crash. It was a clean merger of 2 bodies that gave scientists their first clear proof that dark matter exists. The scientists realized they were seeing the same story on a very different scale when they pointed their telescopes toward the cosmic collision zone. The bullet cluster was the original. This is the follow-up, the more complicated and huge version of the same story with 4 paths. If the bullet cluster were a bullet, this would be a nuke. The bullet cluster earned its fame because it provided one of the most elegant natural experiments in astrophysics. 2 galaxy clusters collided about 3.8 billion light-years away, and the aftermath revealed something astonishing. The hot gas, visible in X-rays, had slowed and clumped together, while the galaxies and their invisible dark matter halos passed straight through. The separation between the 2 components proved that most of the cluster's mass couldn't be normal matter. The collision essentially peeled gravity apart from visible light, showing us where dark matter truly resides. The cosmic collision zone follows the same physics, but on an exponentially larger scale. Instead of 2 clusters, it's 4, each the size of or larger than the bullet cluster itself. Instead of one shock front, there are multiple overlapping waves spreading through plasma at millions of kilometers per hour. And instead of a simple 2-dimensional map of matter, there's a tangled 3D structure with layers of galaxies, gas, and dark matter all moving on different trajectories. It's the same experiment, but performed in chaos. A universe-sized stress test for every model of cosmic structure we have. Comparing the 2 reveals how cluster mergers evolve across cosmic time. The bullet cluster represents a relatively young collision. 2 clusters that hit head-on and are now drifting apart, with their dark matter halos still distinct. The cosmic collision zone, in contrast, is an older and more complex system. Some of its subclusters have already begun to merge, while others are just arriving. The scene we observe today is like catching 4 car crashes happening simultaneously at an intersection, each at a different angle, each leaving its own debris trail. This makes it not only larger but more instructive. It shows multiple collision phases at once. In X-rays, it is easy to see that the 2 groups are very similar. Both have bow shocks, which are bent, bright fronts formed when plasma is compressed by supersonic motion. Both show peaks that aren't in the same place between gas and dark matter. These signals are not single in the cosmic collision zone, though. They are stacked. Each subcluster has its own shock front, and when they touch, they make patterns in the pressure and temperature that are called interference. Chandra's heat maps look like rings on water that is moving back and forth. The pond is 13 million light-years wide, though. The gravitational lensing patterns add another layer of comparison. In the bullet cluster, the lensing map cleanly separated 2 lobes of dark matter, one for each cluster. Here, lensing reveals a spiderweb of gravitational wells, 4 main concentrations of mass tied together by bridges of dark matter. These filaments act like connective tissue between the cores, stretching and twisting as the merger progresses. The clarity of these maps provides a unique opportunity. They allow astronomers to test whether dark matter behaves identically across vastly different environments. So far, both systems show the same result. Dark matter remains collisionless, unimpeded, and purely gravitational. Scale is also a key cosmic idea that is hidden in the comparison. The cosmic collision zone is thought to have 10 times more mass than the bullet cluster together. In terms of plasma temperature, shock fronts and lensing power, it is better. It's the next step in the history of the universe. It's a combination of mergers, a structure made from smaller crashes that happened over billions of years. It's what happens when the universe starts putting together towers out of its building blocks. The radio arc. The radio arc is one of the most amazing and strange things that has ever been seen in a galaxy cluster. It cuts through the cosmic collision zone like a lightning scar. It's not a galaxy or a string of stars. It's a huge structure made of synchrotron radiation. This is radio light that electrons give off when they pass through very strong magnetic fields, speeding up to almost the speed of light. The arc goes on for several million light years and marks the unseen edges where subclusters crash into each other and send shock waves through the intergalactic plasma. The cosmic collision zone is like a battlefield, and the radio arc is like the bright scar it left behind. It was made by energy itself. The discovery of the arc came through low-frequency radio telescopes like the Very Large Array, VLA, in New Mexico, and later LOFAR in Europe. When astronomers combined the radio data with X-ray maps from Chandra, the correspondence was perfect. The arc traces the same curved boundaries where plasma density jumps sharply. The shock fronts generated by subclusters moving at supersonic speeds. In optical light, the region looks almost serene, galaxies scattered like dust. But at radio wavelengths it bursts into shape, vast filaments and arcs outlining the collision's raw power. These arcs are produced by electrons caught in magnetic turbulence. When the shock waves sweep through, they compress and twist the magnetic fields that pervade the cluster. Electrons trapped in these fields are accelerated to relativistic speeds, emitting radio waves as they spiral along the magnetic lines. The brightness of the arc reveals just how extreme this process is. The particles involved have energies of up to 10 trillion electron volts, comparable to those generated in human-made particle accelerators like the Large Hadron Collider. Except this accelerator spans millions of light years. The radio arc's shape and polarization tell scientists a great deal about the physics behind it. The radio light is highly polarized, meaning the waves oscillate predominantly in one direction. This is a hallmark of ordered magnetic fields, showing that the shock has aligned them across a vast region. The arc's curvature, meanwhile, traces the edge of one of the fastest moving subclusters, likely the bullet-like core racing through the plasma. As it plows ahead, it drives a bow shock that sweeps up magnetic lines and energizes electrons along its path, leaving behind a glowing arc that can persist for hundreds of millions of years. That which makes this curve stand out is how big and clear it is. There are a lot of groups with scattered radio halos or relics, but not many with such a clear, sharp filament. Millions of light years long, from one end to the other, it hints that the shockwave below is one of the biggest ever seen. An experiment shows that these kinds of arcs only appear in the craziest merges, when supersonic cores crash through thick plasma at a speed of 1,000,000 kilometers per second. That's exactly what the cosmic collision zone is like. 4 groups meet, and at least 2 are moving fast enough to cause shocks that can make relics this big. The radio frequencies emitted by the arc are also a clue to its age. Lower frequencies correspond to older, cooling electrons, while higher frequencies trace freshly accelerated particles. By measuring the arc's spectral index, the way its brightness changes with frequency, astronomers can determine how long ago the shockwave passed. The data show a gradient. The outer edge is bright and sharp, while the inner edge fades, suggesting that the shock is moving outward and the electrons behind it are slowly losing energy. In essence, the radio arc is a time-lapse photograph of the collision itself, capturing both the moment of impact and its fading echoes. These emissions also help scientists probe magnetic field strength in the cluster, a quantity notoriously hard to measure. The polarization and intensity of the radio light indicate that the fields are on the order of a few microgauss, comparable to those in spiral galaxies but spread across incomprehensibly larger scales. This confirms that cluster mergers are powerful magnetic engines. capable of amplifying weak primordial fields into cosmic-scale networks that may span the entire observable universe. Colliding gas clouds. The violence in the cosmic collision zone isn't just between dark matter and stars. It's written into the gas that lies between galaxies as well. Huge clouds of cosmic gas, each tens of millions of light-years across, crash into each other at speeds of thousands of kilometers per second. These crashes make more than just heat and shock waves. They also make turbulence, density spikes, and chaotic areas where the building blocks of new stars are squished together to life. The collision's raw physics can be seen in these clouds, where galaxies are being destroyed and new ones being formed. The intergalactic gas in clusters isn't like air, it's plasma, a soup of protons, electrons, and heavier ions heated to over 100 million kelvins. Normally, this plasma sits in a kind of uneasy balance, its pressure keeping galaxies suspended in a thin medium. But when four clusters collide, that balance collapses. Gas from each subcluster slams into the rest, forming enormous compression fronts. These collisions are so violent that they temporarily outshine the light of the galaxies themselves in X-rays. Chandra's images show these bright intersections clearly, overlapping knots of plasma glowing with newly released energy. At these junctions, the gas doesn't just heat, it moves. Streams of plasma twist and shear, mixing hot and cooler material together in a chaotic churn. This turbulence drives the creation of eddies and vortices the size of galaxies, where temperatures and densities fluctuate wildly. The result is a dynamic, ever-changing web of pressure and motion, a cosmic storm that never truly calms. And within that storm, some regions briefly reach the perfect balance for something remarkable: bursts of star formation. When the gas compresses fast enough, local densities rise to the point where clouds can cool and collapse. Normally, the high temperatures in clusters prevent such cooling, but collision-induced shocks create short-lived cooling corridors, narrow regions where gas can radiate energy and condense. Observations from Hubble and Spitzer have revealed several galaxies in the collision zone undergoing intense starbursts, their light dominated by young, massive stars only a few million years old. It's a paradoxical outcome. The same event that strips gas from galaxies also triggers new waves of creation within them. But for most galaxies caught in this maelstrom, the effect is devastating. As they plow through the cluster's plasma, they experience what astronomers call ram pressure stripping, the same force that makes your hand feel resistance when held out of a moving car window. The pressure of the surrounding gas pushes against a galaxy's own gas disk, peeling it away like wind tearing leaves off a tree. Trails of stripped gas follow behind, sometimes stretching for hundreds of thousands of light years. Without this gas, galaxies can no longer form new stars, and over time, they fade into dormant red shells. Radio and optical observations have captured both sides of this process. Some galaxies show vivid blue knots of star formation, triggered by compression. Others display long, wispy tails, the aftermath of stripping, glowing faintly as the ejected gas cools and mixes with the surrounding plasma. These tails can themselves become miniature sites of creation, forming small star-forming clumps known as fireballs, floating independently in the cluster medium. It's cosmic recycling on the grandest scale, destruction feeding creation. The colliding gas clouds also reshape the chemical landscape of the cluster. Each burst of star formation enriches the surrounding medium with heavy elements, oxygen, carbon, iron, produced in supernova explosions. Over billions of years, these metals diffuse throughout the cluster's plasma, seeding future generations of galaxies. The cosmic collision zone is effectively a giant foundry, forging and distributing the materials for planetary systems long before they'll ever form. To understand these processes, you need to look at the cluster at all wavelengths. X-rays show the heat from collisions. Visual and infrared light show the light of new stars. And radio waves pick up the magnetic waves in the plasma. All of these findings show that cluster mergers aren't just terrible events. they're also creative forces that change the way matter moves through the universe. Even though the environment is unfriendly, the crashes push, stir, and fertilize the universe, making sure that matter and energy never stop moving. The fate of its galaxies. Galaxies that are in the cosmic collision zone are barely able to stay alive. All of them, from spirals to huge ellipticals, are being changed, taken, or put out by forces that are much stronger than their own gravity pull. It is here that galaxies go to die, but not by exploding all at once. Instead, they die slowly and painfully through a process called cooling, which takes away the materials needed to make stars. For scientists, this area shows what happens at the end of galactic evolution, when the environment of a galaxy gets too dangerous for it to live. The main culprit is the cluster's superheated plasma, a medium so dense and energetic that it batters every galaxy passing through. As galaxies plunge into the cluster's core, they face immense ram pressure, the drag force from moving through the thick intergalactic gas. This pressure can exceed a galaxy's own gravity, tearing away its gas in long tails that trail behind like smoke. The process is spectacular but tragic. Galaxies that once glowed with blue light from young, massive stars fade into dull red ellipses, their star-forming regions stripped clean. Chandra's X-ray maps and Hubble's optical images show these stripped galaxies in the act, some with gas tails stretching hundreds of thousands of light-years into the surrounding plasma. Once the gas is gone, star formation stops. Within a few 100 million years, the short-lived blue stars burn out, leaving only older, redder stars behind. These galaxies become what astronomers call quenched or red and dead. The cosmic collision zone accelerates this fate dramatically. In normal clusters, quenching might take billions of years. Here, the turbulence and density shorten that timescale by an order of magnitude. The result is a graveyard of galaxies, silent, stripped remnants orbiting the cluster's heart. But not every galaxy is lost. Some people, especially those on the edges of the impact, have short revivals before they fade away. When shock waves and compression fronts come through, they can briefly start starbursts, which causes areas of gas to quickly form stars. Even though these bursts only last a short time, their light shines through the chaos like flames from space. Spitzer's infrared observations and ALMA's radio data have found these short-lived bursts of activity that usually last less than 100 million years. At these times, galaxies shine brighter than ever, as if they were defying the inevitable silence that is coming. Others are transformed rather than destroyed. Spiral galaxies passing through the cluster's dense medium can lose their outer gas but retain their central bulges, gradually morphing into lenticular galaxies, smooth, disc-like systems without spiral arms or active star formation. Over billions of years, the entire population of the cluster evolves toward this form, uniform, red, and quiet. This transformation is not unique to the cosmic collision zone, but the merger's extreme conditions make it happen faster and more violently than anywhere else. Even galaxies that are outside the cluster's core aren't completely safe. Gravitational waves caused by the impact pull and stretch galaxies as they move around the Sun. Some are thrown into space between clusters, where they become orphan galaxies that move around as the cores merge. These people who have been sent away carry tiny streams of stars and dust that show them the way to safety. Others fall inward and merge with the center galaxy, which is getting bigger and will finally take over the cluster. This future supergiant will be made up of the pieces of hundreds of smaller systems. It will be the brightest center galaxy, BCG, of the cluster, surrounded by a halo of faint star debris that will show how destructive the merger really was. The role of ram pressure stripping. Space is very rough in the cosmic collision zone, so galaxies don't just float through it, it tears them apart. Each one is surrounded by a cloud of gas, which is what feeds stars that will come after them. But as these galaxies fall through the thick, very hot plasma of the cluster, the fuel is ripped off. This is called ram pressure stripping. This is one of the most dramatic and beautiful types of cosmic destruction, and it's happening on a scale that has never been seen before in the universe. Think of a galaxy as a ship heading into a storm. It is hit very hard by the intergalactic medium, which is a sea of charged particles. It's not empty here. It's plasma at hundreds of millions of degrees, moving at a speed of several thousand kilometers per second as the substructures of the cluster hit each other. The tearing force gets stronger as the galaxy moves faster and as it enters thicker plasma. The gas in the galaxy's disk is blown away, especially the loosely bound stuff near the edges. This leaves behind long, glowing tails of gas that have been taken away. These tails can be tens of thousands of light-years long, or even longer than the galaxy itself. Chandra's X-ray images show these tails vividly, narrow filaments of cooler, denser gas embedded within the surrounding hot plasma. Hubble's optical data adds detail, revealing star-forming knots along some of them. This means that even as the galaxies lose their gas, parts of that stripped material compress and collapse into new stars. In effect, RAM pressure stripping destroys galaxies while creating small bursts of life in its wake. These fireball regions, bright compact clusters of newborn stars, drift through the cluster like sparks blown from a dying flame. They'll burn briefly before cooling, leaving behind scattered star streams across intergalactic space. The physics behind this process is elegantly simple, first described by astrophysicist Gunn and Gott in the 1970s. The stripping force depends on two main variables: the galaxy's velocity and the density of the intracluster medium. When the pressure of the surrounding gas exceeds the galaxy's own gravitational hold on its internal gas, the material is torn free. In the cosmic collision zone, both conditions are extreme. The plasma density is enormous due to the overlapping subclusters, and velocities are near record-breaking levels, over 3,000 kilometers per second for some galaxies. It's the perfect storm for complete gas removal. This process transforms galaxies both visually and chemically. Spiral galaxies entering the collision with bright blue disks are stripped bare within a few hundred million years, their spiral arms fading into featureless ellipses. The loss of gas halts star formation, shifting their color from blue to red. Over time, entire populations of galaxies evolve this way, turning the cluster's once vibrant population into a field of silent ancient systems. RAM pressure stripping is, quite literally, the sculptor of galaxy morphology in high-density environments. The stripped gas doesn't vanish into the void. It enriches the cluster's intra-cluster medium, ICM, with heavy elements. Supernovae and stellar winds from the galaxies had already seeded their gas with metals like oxygen, carbon, and iron. When that gas is expelled, those elements mix with the surrounding plasma, raising its metallicity. Over billions of years, this enrichment process builds up the complex chemical fingerprint of the cluster, ensuring that future generations of stars, if any ever form again, will be built from recycled material. In this way, even destruction contributes to cosmic evolution. RAM pressure stripping also interacts with the cluster's magnetic fields, producing striking effects seen in radio wavelengths. As the stripped gas moves through the plasma, magnetic lines stretch and twist around it, generating radio tails, faint emissions that trace the paths of gas clouds being carried away. Observations with the Very Large Array and MeerKAT show that some of these radio trails extend for millions of light-years, making them among the largest single structures associated with individual galaxies. They're essentially footprints left behind by galaxies fighting a losing battle against the cluster's atmosphere. The hidden supermassive black holes. Some of the most powerful engines in the universe are working in the cosmic collision zone, where dead galaxies have been stripped of their outer layers. These are giant black holes, which are monsters with millions or billions of times the mass of the Sun. Chaos has woken them up. As a rule, they sleep peacefully in the centers of galaxies when they are low on fuel. Things change, though, when groups hit each other. Streams of gas and dust are moving toward the centers of galaxies after being pushed around by gravity waves and tides. And when that stuff goes over the event horizon of a black hole, it gives off so much energy that it can light up whole galaxies. Astronomers call these awakened giants active galactic nuclei, AGN. and the cosmic collision zone is teeming with them. Observations in radio, X-ray and infrared light show dozens of galaxies here flaring with signs of renewed black hole activity. In X-rays, Chandra detects sharp, point-like sources embedded within the broader glow of hot plasma, unmistakable markers of accretion. In radio wavelengths, jets of charged particles stream from galactic cores, cutting through space like cosmic searchlights. Each one is powered by a black hole spinning so fast that the infalling gas forms a disk heated to millions of degrees before vanishing beyond the horizon. The reason these black holes come alive during cluster mergers is simple. Chaos feeds them. When galaxies collide or experience strong tidal forces, their orbits are disturbed and their interstellar gas is funneled inward. Normally, this gas sits in stable disks around stars, but collisions compress and redirect it toward the core. As it spirals inward, friction and magnetic turbulence heat it to extreme temperatures, releasing radiation across the spectrum. In just a few million years, a blink of cosmic time, a once dormant black hole can flare to life as a quasar, briefly dominating the light output of its entire host galaxy. In the cosmic collision zone, this process plays out on a colossal scale. With 4 subclusters merging simultaneously, gravitational tides are tearing at every galaxy. Many of them, especially those near the dense core of the merger, show double or even triple nuclei, signs that smaller galaxies have merged into them recently, likely triggering renewed accretion. In some cases, 2 supermassive black holes orbit each other in close proximity, slowly spiraling inward. These binary black holes will eventually merge, releasing gravitational waves powerful enough to ripple across millions of light years. The cluster, therefore, isn't just a source of radiation, it's a factory for the universe's most extreme gravitational events. Astronomers studying this region with ALMA and the Very Large Array have detected narrow radio jets extending tens of thousands of light years from several galaxies. These jets are produced when magnetic fields near a black hole's accretion disk channel plasma outward at nearly the speed of light. They pierce the surrounding gas like needles, sometimes carving cavities in the hot plasma that later fill with X-ray emitting material. In composite images, these cavities appear as dark bubbles surrounded by blue glow, clear signs that black holes are sculpting their environment even at intergalactic scales. But these black holes don't just feed and radiate, they also regulate. The energy they inject into the surrounding gas helps prevent it from cooling too quickly. Without this heating, the dense plasma would collapse under its own gravity and trigger uncontrollable star formation. Instead, AGN feedback, the constant push and pull between heating and cooling, keeps the cluster's gas in a delicate balance. The cosmic collision zone is a laboratory for this feedback process, showing how black holes both destroy and preserve, stabilizing the environment even as they devour it. Infrared observations from Spitzer have also revealed dust-enshrouded AGN hidden from optical view, buried deep within stripped galaxies. These obscured black holes are invisible in visible light, but glow brightly in the infrared as surrounding dust absorbs and re-emits their energy. Some of them are likely in the early stages of reactivation, drawing in the first streams of gas released by the ongoing merger. Over the next few 100 million years, many of these will evolve into full-fledged quasars before fading once again into dormancy as their fuel runs out. The presence of so many active black holes in one cluster provides a rare opportunity to study how they grow and interact with their environment. By comparing their luminosity, jet strength, and X-ray output, astronomers can estimate how much matter they're consuming and how efficiently they're converting it into energy. The data suggest that the collision has boosted overall AGN activity by at least an order of magnitude compared to more tranquil clusters. A sign that cosmic violence truly awakens sleeping giants. Cosmic microwave background distortion. The cosmic collision zone affects more than just the area around it. It also leaves marks on the universe's oldest light. This cluster is crossed by the faint glow of the cosmic microwave background, CMB, which is radiation left over from the Big Bang. It takes 13.8 billion years to get to Earth. It changes when it does. The superheated gas and turbulent plasma in the cluster cause a small but measured distortion called the Sunyaev-Zeldovich effect. This effect lets scientists study the cluster's pressure, temperature, and motion in a way that no visual camera could. Here's how it works. The CMB photons streaming through the universe are incredibly uniform, carrying information about conditions just 380,000 years after the Big Bang. But when those photons pass through a region like the cosmic collision zone, they encounter electrons in gas that's hundreds of millions of degrees hot. Some of the photons collide with those fast-moving electrons and gain energy, a process called inverse Compton scattering. As a result, the CMB light gets slightly brighter at higher frequencies and dimmer at lower ones, leaving a faint signature in the microwave sky. To the human eye, it's invisible, but to sensitive instruments like Planck, AKT, and SPT, it's a clear quantitative signal of how much energy the cluster's plasma contains. This distortion reveals more than just temperature. It encodes the pressure profile of the cluster's gas, the way heat and density vary from its core to its outer edges. By measuring how strong the effect is at different points, astronomers can map the three-dimensional structure of the plasma that fills the collision zone. In the cosmic collision zone, these measurements show extraordinarily high pressure, consistent with shock waves moving through the cluster at thousands of kilometers per second. In some regions, the signal even shows asymmetry, indicating that the gas is still in motion and the merger is ongoing rather than settled. A variant of this phenomenon, called the kinematic Sunyaev-Zeldovich effect, offers yet another layer of insight. Instead of changing the CMB's color, it shifts its brightness slightly depending on how fast the entire cluster is moving relative to the cosmic background. When astronomers applied this technique to the cosmic collision zone, they detected subtle shifts that revealed the bulk motion of the gas and the subclusters within it. These measurements confirmed that some substructures are moving at several thousand kilometers per second, still ricocheting through the gravitational field long after the initial collisions began. The beauty of the Sunyaev-Zeldovich effect is that it doesn't fade with distance. Unlike visible light, which weakens with the square of the distance, this microwave distortion depends only on the cluster's total pressure. That means even far-off systems like the cosmic collision zone, more than 5 billion light-years away, can be studied in exquisite detail. Combining CMB data with X-ray observations from Chandra gives astronomers both halves of the equation, the temperature from X-rays and the pressure from microwaves, allowing them to calculate the cluster's total mass and energy content independently of gravitational lensing. What those numbers reveal is staggering. The total thermal energy in the cluster's gas is equivalent to the combined output of 100 trillion suns shining for the entire age of the universe. This energy doesn't just radiate outward, it also affects how other forms of light travel through space. Photons from background galaxies that pass near the cluster are slightly boosted in energy as they interact with its hot electrons. Over cosmic timescales, such interactions add up, contributing to the diffuse microwave glow that permeates the cosmos. The cosmic collision zone is so extreme that it's often used as a benchmark for calibrating CMB studies across the sky. Because its Sunyaev-Zeldovich signal is strong and complex, scientists use it to test models of how clusters evolve and how their internal physics affects large-scale cosmological measurements. Understanding the distortions caused by systems like this helps refine our measurements of fundamental constants, including the Hubble parameter, which describes how fast the universe expands. In other words, by studying how the cosmic collision zone warps ancient light, astronomers can better understand both the local violence of a single merger and the global rhythm of cosmic expansion itself. Another fascinating discovery is that the way the CMB interacts with the plasma in the cluster could help us understand the microphysics of high-energy electrons and magnetic chaos. There are small changes in the effect's range, or wiggles in the data, which show that not all electrons have the same temperature distribution. It's possible that the same shock waves that light up the cluster in X-rays and radio waves speed up some of them, making them much more powerful. Finding these non-thermal parts is hard, but the cosmic collision zone is one of the few places where it is possible because of how bright it is. Mapping velocity with ALMA. This area of space continues to amaze scientists even after decades of study. Scientists were able to map its temperature, mass and shape for many years, but not how it moved. The tens of millions of degrees hot plasma is spread out over millions of light years and doesn't move in neat circles. It flows, swirls, and hits each other like a sea of fire. The Atacama Large Millimeter Submillimeter Array, ALMA, which is one of the most powerful telescopes ever built, was used to directly measure that motion inside the star. ALMA's radio antennas are high up in the Atacama Desert in Chile. They can pick up faint millimeter waves that show very precisely how gas moves inside galaxy clusters. By observing the cosmic collision zone, ALMA achieved something no telescope had before: a detailed velocity map of emerging clusters' plasma. It did this by studying slight shifts in the spectrum of the Sunyaev-Zeledovich effect, the same CMB distortion that reveals temperature and pressure. As the gas moves toward or away from us, those spectral signatures shift ever so slightly due to the Doppler effect. Measuring those tiny changes, only a few parts in a million, allowed astronomers to determine how the plasma flows within the cluster. The result was a portrait of motion, not just structure. Rivers and whirlpools of gas flowing through space, sculpted by gravity and shock waves. What ALMA found confirmed just how violent this system remains. The gas isn't static or settling down, it's still in motion, even billions of years after the first collisions. Whole regions of plasma move at several thousand kilometers per second, colliding head-on with opposing flows. These velocities are among the highest ever recorded within a galaxy cluster. The patterns reveal a vast rotating turbulence. Hot gas streaming around dark matter cores, mixing and colliding in ways that continually reshape the cluster's internal structure. This motion explains why the temperatures remain so high. Kinetic energy from the merger is still being converted into heat through turbulent dissipation. ALMA's resolution also allowed astronomers to separate the movements of different subclusters. Some appear to be receding, others approaching, each dragging its own tail of gas. The data show that these motions are not random, but structured, the remnants of multiple collision paths. By comparing ALMA's velocity field with gravitational lensing and X-ray maps, scientists can reconstruct the 3D choreography of the entire merger. It's like rewinding a cosmic explosion in slow motion, tracing each fragment's trajectory to understand how the catastrophe unfolded. The new measurements also revealed smaller-scale features that had never been seen before: localized vortices and eddies within the plasma, the cosmic equivalent of atmospheric storms. These turbulent zones may play a key role in distributing heat and magnetic energy throughout the cluster. Where the gas flows converge, the turbulence stirs magnetic fields, amplifying them through the same dynamo effect that powers magnetic structures in galaxies. This process could explain why the cluster's radio relics and halos remain so bright. The turbulence keeps reaccelerating electrons long after the initial shocks have faded. The differences in pressure and speed seen near the subclusters that are moving quickly are even more compelling. ALMA's data show huge shear zones, which are places where layers of gas slide past each other quickly, causing friction and instability. It's likely that these forces cause Kelvin-Helmholtz waves, which are patterns of ripples at the edges of gases that are moving. These kinds of traits have been seen in the atmospheres of planets and the remains of supernovae, but it has never been seen on the scale of a cluster. It seems to say that the basic mechanics of fluids control both small and large objects. These findings have huge effects on how scientists think about how clusters evolve. Until recently, most models thought that mergers would quickly reach balance after the big collision was over. The results from ALMA show that this is not true. The cosmic collision zone is still very young in terms of dynamics. and gas flows and turbulence keep it moving all the time. It could take billions of years longer for the system to fully settle down into a stable spherical cluster. Until then, its internal energy will keep swirling, feeding magnetic fields, speeding up particles, and keeping the region's X-ray and radio wave brightness very high. ALMA's velocity mapping also improves mass estimates. By combining motion data with gravitational lensing, astronomers can separate thermal pressure from heat and dynamic pressure from motion. This allows for more accurate calculations of how much dark matter must be present to keep the cluster bound. Early results suggest that the total mass might be even higher than previous models predicted, possibly approaching 2 quadrillion solar masses. That makes the cosmic collision zone one of the most massive gravitational systems ever discovered, second only to the largest known superclusters in the observable universe. Lessons in cosmic evolution. The cosmic collision zone isn't just a show about space, it's also a school for the world. We can learn something important about how cosmic structures form from every color of light, every map of temperature and motion, and every gravity lensing pattern. This kind of galaxy cluster is not a fixed memorial. It is a live thing in cosmic time that is still putting itself together through gravity's slow and violent dance. Scientists have learned a lot about how the universe's biggest structures have changed over time by studying this one crash. They have learned about how they were formed in the early universe and how they ended up in an expanding universe dominated by dark energy. The first and most obvious lesson is that chaos builds order. What appears as pure destruction, clusters smashing together, galaxies stripped bare, plasma boiling, is actually the mechanism by which structure emerges. Every major galaxy cluster we see today, including our own local group's eventual successor billions of years from now, was built through a sequence of mergers like this one. Gravity gathers smaller systems, merges them violently, and allows them to settle into larger, more stable configurations. The cosmic collision zone captures this process mid-act, showing the messy reality of how cosmic architecture takes shape. The second lesson concerns energy transformation. In these colossal mergers, kinetic energy from motion is steadily converted into heat, radiation, and turbulence. ALMA's velocity maps, Chandra's X-ray data, and radio relic observations together form a complete energy ledger, tracking how gravitational potential energy becomes thermal plasma and relativistic particles. This chain of conversion is universal. It governs the behavior of everything from supernova remnants to accretion disks to galaxy clusters. The collision shows that the same physical laws apply on vastly different scales, uniting the small and the immense under one set of rules. Third, the cluster offers a window into dark matter dynamics. Because the plasma, galaxies, and dark matter all respond differently during collisions, scientists can use their separation to test models of how dark matter behaves. The cosmic collision zone has confirmed once again that dark matter is collisionless. It passes through both gas and other dark matter without friction. Yet its gravitational influence holds the entire structure together, proving that it dominates cosmic mass, even in the most violent environments. In this way, the cluster serves as both experiment and evidence, a real-world testbed confirming the invisible framework that supports the visible universe. A fourth insight lies in how magnetic fields and turbulence evolve. Before this discovery, astronomers knew that galaxy clusters contained magnetism, but not how it formed or persisted. The cosmic collision zone shows that merging events themselves are cosmic dynamos. As subclusters crash and mix, they amplify primordial magnetic fields, turning weak, disordered strands into powerful, organized networks that stretch across millions of light years. These fields, in turn, regulate how heat moves through the plasma and how cosmic rays travel through space, processes that shape not just this cluster, but every galaxy within it. The collision also teaches us about galactic ecology, the life cycle of galaxies within large structures. Here, in one snapshot, we see every stage, young galaxies igniting brief bursts of star formation in compressed gas, others stripped bare and fading into elliptical silence, and still others torn apart entirely. This diversity shows that the environment, not just age or mass, dictates a galaxy's fate. The denser and more turbulent the environment, the faster galaxies lose their gas and transform. Over cosmic time, clusters act as engines of galactic aging, turning once spiral-rich populations into collections of red, quiescent ellipticals. From a cosmological perspective, the cosmic collision zone also highlights the role of hierarchical formation. The idea that small structures form first, then merge to create larger ones. This principle, predicted by the LCDM, Lambda Cold Dark Matter model, underlies modern cosmology. Observing a multi-merger like this validates that picture on an unprecedented scale. The same gravitational physics that built this cluster will, given time, merge clusters into superclusters and superclusters into filaments, the vast cosmic web that defines the universe's shape. The impact zone shows time changing, which is probably the most important thing it does. It's set in time about 5 billion years ago, when dark energy was just starting to speed up the growth of the universe. It happened at the right time in history, early enough to show how quickly clusters grow, but late enough to show how dark energy slows down more assembly. Over the next eons, similar crashes will happen less often, because the growth of the universe will separate structures from each other. So, the cosmic collision zone is both a reminder of a universe that was more linked and a sneak peek at what little large-scale change is still going on. A natural laboratory for plasma physics. The cosmic collision zone is not only a wonder of the universe, but also one of the best places to study natural plasma. The temperatures, sizes, and forces at play here could not be found anywhere else on Earth. In this huge area where galaxy clusters are merging, matter is in its most basic form, plasma. Plasma is a sea of charged particles that have lost their electrons and are moving because of gravity, magnetism, and chaos. Every shockwave, filament, and flare in this cluster is a test of how plasma behaves that spans millions of light years. When scientists study it, they can test the laws of nature in harsh conditions that no machine made by humans can reach. At first glance, the environment seems simple. Gas heated to hundreds of millions of kelvins. But plasma behaves very differently from ordinary gas. It doesn't just flow, it conducts electricity, responds to magnetic fields, and can generate waves, currents, and instabilities. In the cosmic collision zone, all of these effects happen simultaneously on scales so enormous that even supercomputers struggle to simulate them. The magnetic fields twist and fold. Shock fronts ripple through ionized hydrogen, and turbulent flows create eddies that stretch across thousands of light years. Observing this chaos reveals how energy moves and transforms in plasma, how it's transported, dissipated, and sometimes explosively released. One of the most important discoveries here concerns turbulent mixing. In laboratory plasma, turbulence quickly equalizes temperature and density differences. But in this cluster, Chandra's X-ray data show regions where temperature varies sharply over short distances, meaning turbulence behaves differently at cosmic scales. Magnetic fields likely play a role, channeling motion along narrow filaments and preventing heat from spreading evenly. This helps explain why the plasma remains so hot and uneven billions of years after the initial collisions. Magnetic confinement keeps it stirred but not smoothed. Collisionless shock creation is another noteworthy feature. Shocks happen in air or water on Earth when molecules bump into each other and trade energy. But the plasma in the cosmic collision zone is so empty that it's rare for particles to hit each other directly. Instead, shocks happen when electromagnetic waves, waves of electric and magnetic force, interact with each other and squeeze the plasma without touching it. Looking into these shocks teaches us about basic plasma physics that is useful for understanding supernova remains, solar flares, and even fusion plants. Even though the process happens everywhere, it's only here that we can see it happen over millions of light years. The cluster's vast magnetic web also gives researchers a chance to study magnetohydrodynamic (MHD) turbulence, the complex interplay between fluid motion and magnetic fields. In regions of intense shock activity, plasma flows stretch and fold magnetic lines, amplifying their strength through the dynamo effect. This mechanism may explain how weak primordial magnetic fields from the early universe grew into the structured, large-scale fields we observe today. By comparing radio polarization data from the cluster's relics and halos with simulations, scientists can see how MHD turbulence evolves over time, how energy cascades from large eddies down to microscopic scales, where it dissipates as heat. The cosmic collision zone also challenges our understanding of particle acceleration. Most of the electrons responsible for its radio glow have energies far higher than can be explained by thermal processes alone. The leading theory is stochastic acceleration, where turbulent magnetic fields re-energize electrons randomly, giving them repeated boosts. These processes are similar to what happens in the solar wind or Earth's magnetosphere, but here they occur on cosmic scales, offering a bridge between astrophysics and plasma laboratory physics. Every radio relic, every arc of synchrotron light, is essentially a record of plasma turbulence, sculpted by gravitational forces. Astronomers and physicists are working together to apply these findings to practical questions. For example, understanding how energy transfers in collisionless plasmas could help improve fusion confinement methods on Earth. Fusion devices like tokamaks and stellarators rely on magnetic fields to control hot plasma. The same physics at work here, just on a much smaller scale. Studying the cosmic collision zone is like observing the ultimate tokamak in nature, where the laws of magnetism, heat transport, and turbulence can be measured directly through radiation instead of sensors. Even cosmic rays, the high-energy particles that constantly bombard Earth, find their origin in similar environments. The shocks and turbulence seen here are capable of accelerating protons and electrons to energies beyond what human technology can achieve. Understanding how that acceleration works in the cluster helps explain how cosmic rays propagate through galaxies and intergalactic space, linking the physics of clusters to the radiation environment of our own planet. There are a lot of ways that the cosmic collision zone blurs the line between plasma physics and astronomy. Things like cosmic magnets, shockwaves in stars, and chaos in space weather are all linked by its conditions. Every measurement and spectrum map adds a new piece of information to the language of plasma that cosmologists and experimental physics can both understand. The strange alignment problem. There are rules in the cosmic collision zone, or at least there should be. On this big of a scale, gravity should be in charge, leading galaxies and clusters along known paths through the cosmic web. But when scientists looked closely at this area, they found something strange. Some of the subclusters aren't moving the way gravity says they should. Their angles and directions look a little off, which could mean that there are forces or conditions at the start of the impact that we can't see that break the symmetry. The alignment problem is what has made the cosmic collision zone from a case study in astronomy into a problem for cosmology itself. When scientists mapped the velocities of galaxies within the cluster using spectroscopy and ALMA's Doppler measurements, they expected to see motion mostly along 2 or 3 primary axes, paths that line up with the dark matter halos and the gravitational center of mass. Instead, the data revealed multiple subclusters moving at oblique angles, even perpendicular to one another. Some seemed to veer away from the gravitational center instead of toward it. Others followed arcs that suggested lateral movement, as if deflected by invisible hands. On smaller scales, streams of gas and galaxies appeared misaligned with their own dark matter concentrations. These inconsistencies were too large to dismiss as random noise. Something about this collision didn't add up. There are several possible explanations, and none of them are simple. One idea is that the cluster is embedded in a cosmic filament, a massive strand of the universe's large-scale structure, oriented at an angle to our line of sight. The collisions we see, might actually be happening in 3 dimensions, with some clusters plunging toward us while others move sideways or away. The projection of those motions onto the plane of the sky could create the illusion of misalignment. However, even accounting for that, the degree of deviation remains unusually high. Another hypothesis is that off-axis collisions occurred earlier in the cluster's history. Instead of a single, clean head-on merger, the subclusters may have collided at skewed angles, leaving residual angular momentum that continues to twist their orbits. In such a scenario, the entire structure could be rotating, slowly but measurably, like a vortex of galaxies. Simulations suggest that if the original collision angles were just a few degrees off, the resulting motion could persist for billions of years, creating the kind of asymmetry we see today. But some experts have come up with a more remarkable idea. The misalignment might show us something new about the science of dark matter. In most models of the universe, dark matter doesn't interact with anything other than gravity. But if dark matter particles occasionally interact with each other by bouncing off of each other very slightly, their halos might get messed up or moved around when they collide at high speeds. This would cause dark matter to behave in a way that isn't expected, pulling galaxies along tracks that aren't lined up right and leaving lensing maps with weak but noticeable errors. The cosmic collision zone is one of the best places in the world to look for these kinds of effects because it has a lot of energy and a lot of impacts. When gravitational lensing maps of the region were compared to X-ray and radio data, astronomers found that the dark matter peaks didn't perfectly line up with the visible subclusters. In some cases, they trailed behind or appeared shifted sideways, implying that the dark matter halos might have been influenced by more than just gravity. The magnitude of these offsets is small, only tens of thousands of light years, but statistically significant. If confirmed, they could provide the first real hints that dark matter has internal properties beyond pure gravitational attraction. That would revolutionize particle physics and cosmology alike. There's also an alternative, more conservative explanation: turbulent feedback from the plasma itself. The immense pressure from superheated gas could create localized buoyant forces, pushing on galaxies and altering their apparent trajectories. These effects would be secondary to gravity, but still strong enough to introduce small misalignments. Some of the most energetic radio relics correspond exactly with regions of unusual motion, supporting the idea that turbulence and magnetic fields may subtly influence how mass moves through the cluster's core. To unravel the mystery, astronomers are combining data from multiple instruments: Hubble for gravitational lensing, Chandra for X-rays, ALMA for velocity fields, and the James Webb Space Telescope for infrared mass tracing. Together, these observations form a kind of 4-dimensional map: position, velocity, temperature, and time. The hope is that by reconstructing the merger's full 3D geometry, scientists can determine whether the apparent misalignment is a projection effect or genuine evidence of new physics. Astronomers are having to improve their knowledge of how star groups change because of the alignment problem. It helps them remember that the universe isn't always smooth or even at tens of millions of light years across. Even though gravity may be the main builder, chaos, magnetism, and maybe even strange matter can change the plans. Already well known for its strength and complexity, the cosmic collision zone may now hold something even more important: a sign that the rules we thought controlled the universe may need to be changed. Relativistic particle acceleration. Between millions of light years, space itself has turned into an engine in the cosmic collision zone. It is a huge natural particle generator. Machines made by people, like the Large Hadron Collider, can throw particles through tubes a few kilometers long at speeds close to light speed. This cluster, on the other hand, does the same thing using only gravity, turbulence, and magnetic chaos. Here, electrons are hurtling through magnetic fields that are being violently bent by the collisions that are happening all the time. As a result, they are giving off synchrotron radiation that can be picked out in the radio spectrum. This is a clear sign that particles are moving at relativistic speeds. Astronomers first suspected this immense acceleration decades ago, when faint radio halos were detected filling the space between galaxies. But it wasn't until detailed radio observations of the cosmic collision zone that the full scope of this process became clear. The cluster's radio arcs, relics, and halos are powered by electrons accelerated in shock fronts. Enormous supersonic boundaries formed when subclusters plow through one another. These shocks compress the plasma, amplify magnetic fields, and launch electrons into repeated cycles of acceleration, a process known as diffusive shock acceleration, DSA. In DSA, charged particles bounce back and forth across the shock front, each time gaining a fraction of energy from the difference in plasma velocity on either side. After enough crossings, an electron's energy can increase by factors of millions, pushing it into the relativistic regime. The faster and stronger the shock, the more efficient this acceleration becomes. In the cosmic collision zone, where subclusters move at thousands of kilometers per second, the conditions are near perfect. The magnetic field strong, the turbulence constant, and the shock surfaces vast. It's the ultimate cosmic particle factory. The result of this acceleration is visible in the radio spectrum. The cluster's relics and halos emit non-thermal radiation, light not tied to temperature, but to motion. By analyzing how brightness changes with frequency, astronomers can estimate how energetic the electrons are and how long they've been traveling. In some areas, the spectrum reveals freshly accelerated electrons, their energy still peaking near the shock fronts. Farther from those fronts, the spectrum steepens, evidence that the electrons have lost energy over tens of millions of years, radiating it away as synchrotron light. This gradient forms a time map of the collision's energy release, showing where acceleration is still happening and where it has faded. But shocks aren't the only accelerators in play. The merger also creates a turbulent cascade, waves and eddies of plasma that constantly stir the magnetic fields. Within this turbulence, electrons can be re-energized through stochastic acceleration, where random magnetic fluctuations act like invisible paddles, kicking particles up to higher energies again and again. This keeps the cluster's radio glow alive long after the initial collision should have cooled. Observations show that even regions far from major shock fronts still emit strongly, proof that turbulence alone can maintain a steady population of relativistic particles. These processes make the cosmic collision zone one of the best natural laboratories for understanding cosmic ray production, the origin of the high-energy particles that permeate the universe and occasionally strike Earth. The same mechanisms operating here likely power cosmic rays in supernova remnants and around black holes. By studying how efficiently this cluster accelerates electrons and protons, scientists can estimate how much of the universe's total high-energy background comes from cluster mergers like this one. Some estimates suggest that up to a quarter of all extragalactic cosmic rays may originate from events of this kind. ALMA and the Very Large Array, VLA, have even detected hints of polarization within the radio relics, showing that the magnetic fields guiding these electrons are surprisingly coherent. This alignment indicates that shocks can organize chaotic fields, focusing the acceleration process along well-defined paths. Where the fields are most ordered, particle acceleration is strongest, forming bright filaments that trace the boundaries of the collision, like glowing veins of energy. Surprisingly, computer models show that these processes may speed up not only electrons, but also protons to energies higher than 108 electron volts, which is close to the energies of cosmic rays found close to Earth. If what they say is true, the cosmic collision zone isn't just a beautiful light show. It's one of the biggest particle engines in the universe, much bigger than anything humans could ever build. Yet even this efficiency has limits. As electrons radiate synchrotron light, they lose energy quickly, and without continuous reacceleration, they fade within tens of millions of years. This balance between acceleration and loss shapes the cluster's radio spectrum, determining how long the relics and halos remain visible. It also hints at how clusters evolve, bursts of acceleration lighting them up briefly, followed by long, dim intervals of quiet before the next merger reignites them. For physicists, the cosmic collision zone is a gift, a full-scale cosmic laboratory revealing how turbulence, magnetism, and shock physics produce the energetic particles that fill intergalactic space. For cosmologists, it's a key to understanding how the universe distributes energy, converting gravitational motion into radiation and heat. And for everyone who looks up at the sky, it's a reminder that the cosmos is not a silent void, but a place of constant motion, a universe that still crackles with the energy of its own making. Light echoes from distant galaxies. The world seems to have a calmer side, even when the cosmic collision zone is the place where everything is going crazy. Light from galaxies billions of light years away bends its way toward us through clouds of plasma, shockwaves, and dark matter. Because the cluster has so much gravity, these echoes are amplified and warped. They are not from the crash itself, but from when galaxies were younger. The mass of the cluster is tangled up, making it look like a huge cosmic screen. It reflects and boosts light from long ago that would be too weak for any camera to see otherwise. This phenomenon, a consequence of gravitational lensing, transforms the cosmic collision zone into one of the most powerful natural telescopes in the universe. Each subcluster acts like a different lens, bending light from background galaxies into multiple images and arcs. Together, the overlapping gravitational fields of the four merging clusters create a lens so complex that it produces dozens of distinct magnified zones, some amplifying light by factors of 100 times or more. In Hubble's deep field exposures, these appear as ghostly, elongated streaks and smudges weaving through the foreground galaxies, snapshots of the universe's youth captured in the middle of cosmic destruction. What makes these light echoes so valuable is their age. Many of the background galaxies seen through this cluster are among the most distant ever recorded, their light traveling for more than 13 billion years before reaching us. That means astronomers are looking back to a time less than a billion years after the Big Bang, an epoch when galaxies were still assembling, stars were forming in furious bursts, and the first heavy elements were spreading through space. Without the cosmic collision zone's gravitational magnification, these galaxies would remain invisible, buried beneath the limits of even the most sensitive instruments. The combination of Hubble's visible and near-infrared imaging with Spitzer and James Webb Space Telescope (JWST) data has turned this region into a treasure map of early cosmic history. JWST's infrared eyes, in particular, can see light stretched by cosmic expansion into longer wavelengths. Through the cluster's lens, JWST has detected galaxies with redshifts beyond 10, meaning their light left them when the universe was less than 500 million years old. Some are tiny, irregular systems only a few thousand light-years across. Others are surprisingly massive for their age, challenging theories of how quickly galaxies can grow. Each magnified image acts like a zoomed-in window into the distant past. The distortions created by the cluster also allow astronomers to reconstruct the original shapes of these faraway galaxies. By modeling the gravitational field of the cluster, using lensing data from Hubble and mass maps derived from ALMA and Chandra, scientists can reverse the bending effect, essentially unwarping the light. This mathematical delensing process produces corrected images that reveal the true structure of the distant galaxies: clumps of star formation, faint spiral arms, and diffuse halos of gas. It's a painstaking task, but it transforms chaos into clarity, turning the cosmic collision zone into both subject and instrument of discovery. These light echoes also help us learn more about how dark matter is spread out. Because gravitational lensing is based on total mass, not just visible mass, the exact placement of each lensed picture shows how the dark matter is distributed in the cluster. The most accurate way for scientists to map the secret mass is to measure very small changes in position and brightness. The cosmic collision zone is both a window into the past and a look into the present that we can't see. It shows how dark matter shapes the paths of light across the universe. The difference between these sounds might be the most wonderful thing about them. In the center, galaxies are merging, gas is heating up, and magnetic fields are twisting. In the background, there is a faint glow of creation, where galaxies are still young but are making their first stars. Everything from cosmic death and birth to destruction and creation can be seen in the same field of view. The same gravity forces that are breaking up nearby galaxies are also showing us the oldest galaxies that ever existed. The time delays between multiple lensed images of the same distant galaxy offer yet another tool. They can be used to measure the expansion rate of the universe. Light from one path may take slightly longer to reach Earth than another, depending on the curvature of spacetime along its route. By comparing these delays with models of the cluster's mass distribution, astronomers can refine their estimates of the Hubble constant, the very rate at which the cosmos expands. Every photon that passes through the cosmic collision zone carries two stories, one of the violence it encountered on its way through, and one of the ancient light it brings from beyond. Together, they turn this cluster into a cosmic archive, a place where the past and present of the universe overlap in the same beam of light, using the collision as a window to the early universe. Not only is the cosmic collision zone a place where things are crashing apart, it's also one of the best places to look at the sky. By making the weak light of galaxies from the beginning of time brighter, it helps scientists learn about how the universe's first structures formed, changed over time, and shaped everything that came after. This cluster is kind of like a telescope and a time machine at the same time. It's a jumbled foreground lens that makes the quiet start of the universe louder. Every major space observatory, Hubble, Spitzer, Chandra, and most recently the James Webb Space Telescope, JWST, has used this region to peer farther back in time than ever before. The cluster's gravitational lensing power transforms it into a cosmic magnifying glass, bending and focusing light from galaxies that formed when the universe was less than 1 billion years old. Behind the glowing plasma and colliding galaxies lies a treasure trove of magnified galaxies, some of the faintest and oldest ever seen. Without the collision's extreme gravity, most of these galaxies would remain hidden beyond the reach of any instrument. Hubble's Frontier Fields program first took advantage of this natural telescope, combining deep optical and infrared imaging with gravitational lensing models to detect hundreds of galaxies at extreme distances. Each elongated arc in those images represented light that had traveled for over 13 billion years before being warped and amplified by the cluster's gravitational field. For astronomers, this wasn't just a visual marvel, it was data. These galaxies showed how quickly stars formed after the cosmic dark ages ended, and how the first heavy elements began spreading through the intergalactic medium. Then came JWST, whose infrared capabilities extended the reach of this cosmic window even further. Through the cosmic collision zone, JWST has captured galaxies with redshifts above 10, meaning their light dates back to when the universe was only about 400–500 million years old. These early galaxies appear surprisingly bright and massive, suggesting that star formation in the early universe was faster and more efficient than models predicted. Some show evidence of primitive spiral structures or compact bulges, features that shouldn't exist so early, at least according to standard cosmological simulations. The data imply that galaxy assembly may have started sooner and progressed more vigorously than expected, forcing scientists to rethink parts of the cosmic timeline. This collision, therefore, doesn't just illuminate the past, it challenges our theories of it. The sheer number of early galaxies revealed behind the cluster suggests that massive star-forming systems were common in the universe's first few 100 million years. That abundance is difficult to reconcile with existing models of structure formation, which predict slower growth, limited by cooling rates and dark matter collapse. By studying these magnified systems, astronomers are refining their understanding of how the first galaxies collected gas, ignited nuclear fusion, and began enriching the cosmos with heavier elements like carbon, oxygen, and iron. The cosmic collision zone also provides a unique vantage point for studying reionization. the era when ultraviolet radiation from young stars and black holes ionized the neutral hydrogen that filled the early universe. Many of the distant galaxies seen through the cluster appeared during or just after this epoch, around 13 billion years ago. Their light reveals how quickly reionization spread and which sources, galaxies or quasars, contributed most to it. Because the cluster magnifies them, astronomers can study their individual properties in far greater detail than would otherwise be possible, measuring their temperatures, chemical compositions, and star formation rates. Gravitational lensing models of the cosmic collision zone have even revealed multiple images of the same ancient galaxy, produced as light follows different paths through the warped space-time around the cluster. These repeated images arrive at Earth at slightly different times, separated by days or weeks. By measuring these time delays, scientists can refine estimates of both the cluster's mass and the Hubble constant, which describes the universe's rate of expansion. In this way, a collision that began billions of years ago helps modern cosmology measure how quickly the cosmos grows today. The most meaningful thing about using this cluster as a window might be both psychological and scientific. It turns disaster into clarity. The same force of gravity that pulls galaxies apart in small areas also concentrates light from the very beginning of the universe. What makes the cluster useful is the damage that makes it glow. Every arc, smudge, and streak in its picture is a link between two times: the present, which is violent, and the beginning, which is fragile. Astronomers will keep an eye on this area with JWST and other telescopes in the future, such as the Nancy Grace Roman Space Telescope. These tools will look for even fainter, smaller galaxies that are boosted by the complex gravity field of the cluster. They will go further back in time to the first few 100 million years after the Big Bang. Any lesson we can learn from the cosmic collision zone is that the universe's beginnings can be found in strange places, sometimes hidden by a storm of destruction so strong that only gravity can show what's beyond it. The birth of a supercluster. Even though the cosmic collision zone looks like a mess right now, all of that chaos is leading to one thing: the birth of a single huge supercluster that will last longer than almost everything else in its area. Today, we're seeing a picture of that process in the middle of its formation. 4 galaxy groups that are locked in a gravitational hug and are slowly coming together to form a single structure. Over billions of years, dark matter, gas, and galaxies fall deeper and deeper into a gravity well. This change is slow, violent, and beautiful. Each of the 4 merging clusters carries hundreds of galaxies, trillions of solar masses of hot gas, and vast halos of dark matter. As they interact, their trajectories spiral inward, losing momentum through gravitational drag and tidal effects. The plasma between them collides first, heating to hundreds of millions of degrees, while the galaxies, mostly empty space between them, pass through relatively unscathed. Over time, gravity pulls everything back together, binding the fragments into a new, larger equilibrium structure. When that happens, the cosmic collision zone will no longer be a battlefield, but a single, mature supercluster, glowing in X-rays and surrounded by a faint, magnetized halo. Simulations show how this will unfold. As the cores of the subclusters merge, the shock fronts, those bright arcs of heated gas we see today, will fade. The plasma will gradually settle, its turbulence decaying into smoother flows. The dark matter halos will overlap, coalescing into a single gravitational center. Galaxies now flying on chaotic paths will fall into stable orbits within the merged potential well. The process may take 5 to 10 billion years, long enough that by the time equilibrium is reached, the universe's expansion will have slowed the inflow of new material almost to zero. The final supercluster will be one of the most massive bound objects in the universe, containing perhaps 2 quadrillion solar masses or more. To put that in perspective, it will outweigh the Milky Way by a factor of several million. Its diameter could exceed 20 million light-years, making it a true cosmic metropolis of ancient red galaxies and thin streams of intracluster light. Those faint bridges of stars, torn from their parent galaxies by earlier tides, will form a diffuse glow stretching between the major galactic concentrations, a kind of stellar fog that fills the cluster's interior. At its heart will reside a single dominant brightest cluster galaxy, BCG, formed by successive mergers of the central galaxies from each subcluster. This future BCG will likely span hundreds of thousands of light years, containing trillions of stars and a supermassive black hole weighing tens of billions of solar masses. The black holes from each of the original cores will merge in sequence, producing bursts of gravitational waves that ripple across the cosmos. These waves will be faint but detectable to future observatories, echoes of the cluster's long consolidation into one. Once the merger is complete, the new supercluster will enter a phase of relative calm. The temperature of its gas will stabilize, star formation within its galaxies will all but cease, and the once turbulent plasma will settle into hydrostatic equilibrium, a delicate balance between pressure and gravity. The cluster's X-ray glow will persist for trillions of years, slowly fading as the gas cools and radiates its remaining heat into space. The magnetic fields, stretched and amplified by the earlier chaos, will remain frozen into the plasma, preserving the memory of the collision long after its visible remnants have disappeared. Cosmic expansion will gradually isolate the supercluster from the rest of the universe. As dark energy drives galaxies farther apart, fewer and fewer external systems will fall into its gravitational reach. Eventually, the cosmic collision zone, or what's left of it, will drift alone in an expanding void. Distant clusters will recede beyond the cosmic event horizon, becoming forever unreachable. Within another 100 billion years, this supercluster will stand as a lonely island of matter, surrounded by blackness. Its galaxies, dimmed by age and distance, will be the only visible objects in its sky. In a way, this kind of violence makes things last. The same gravity forces that broke galaxies apart and turned plasma into storms are now building the strongest structure that can last. In a very far future, when all the stars in the Milky Way have died out, this supercluster will still have its shape. It will be a memorial to the cosmic crashes that made it. The last beacons of a fading universe. The rest of the universe will look very different when the cosmic collision zone has been stable for a very long time and turned into a huge supercluster. Galaxies that are too far away for dark energy's pull will have crossed over the cosmic event horizon and been taken away forever by its constant growth. Not a single new cluster will form. Once full of strands and nodes, the big web of the universe will thin out until only superclusters like this one are left, floating in a sea of darkness that never ends. And among them, the piece of this very old impact will be one of the last signs of matter that can be seen in the world. The forces that created it will have long quieted. The turbulent plasma will settle into equilibrium, its shock fronts gone, its temperature slowly declining over trillions of years. Without fresh infall from surrounding regions, the cluster's hot gas will cool and condense in pockets, forming faint streams that drift inward toward the center. There, the largest galaxy, the merged product of countless earlier collisions, will dominate. It will be a vast elliptical giant hundreds of thousands of light years across, containing trillions of dim red stars and a supermassive black hole so immense that nothing within thousands of light years can escape its pull. By this distant epoch, star formation in nearly every galaxy will have ceased. The hydrogen and helium that once fueled new suns will be locked inside old stars or lost to the cluster's plasma. The existing stars will burn their last reserves of fuel, fading into red dwarfs and then cooling into black dwarfs, dark, degenerate remnants that no longer shine. The supercluster will glow faintly in infrared light, its brilliance reduced to a whisper. Yet in the cosmic night, even that faint whisper will stand out. Across vast distances, any remaining observers, if any could exist, would see this structure as one of the final points of light in the universe. As eons pass, Gravitational interactions will slowly merge many of the surviving galaxies into the central colossus. Each merger will feed its supermassive black hole, releasing bursts of energy as infalling gas heats up before disappearing beyond the event horizon. Occasionally, gravitational wave bursts from merging black holes will ripple outward, faint and fleeting, marking the last moments of dynamism in an otherwise still universe. These waves will travel endlessly, though in time, even they will redshift beyond detectability as the fabric of space-time stretches. The universe will grow so large and empty that light from other superclusters can no longer reach this one. The cosmic collision zone's descendant will become a cosmic island, gravitationally bound and self-contained. Within its invisible dark matter halo, everything that will ever exist in its region of space is already there: stars, planets, black holes, and the last remnants of intergalactic gas. Beyond it lies a horizon not of distance, but of time, space expanding faster than light can cross. Even in that isolation, the supercluster will remain stable. Dark matter will keep it bound, and its central black hole will continue to grow, feeding on whatever matter drifts too close. Over unimaginable timescales, black holes will begin to dominate the cluster's mass budget. When the last star fades, their Hawking radiation will be the only light left, faint quantum sparks escaping from horizons that slowly evaporate. The cosmic collision zone, once a cauldron of creation and destruction, will have become a quiet island of black holes evaporating into the dark. This faraway fate connects the violent birth of the cluster to the universe's final fate. The energy it released when it crashed will eventually fade away, but the buildings it built will last for a very long time. In the beginning, gravity brought together 4 different galaxy clusters. In the end, it will turn them all into one lasting memorial to gravity, a supercluster shining dimly in a mostly dark universe. Testing the limits of cosmology. Not only does the cosmic collision zone show us the past or the future, but it also makes us question everything we think we know about how the world works. Its size, power, and complexity push the limits of astronomy, making scientists test and sometimes rethink the rules that have been used for 100 years to explain matter, energy, and gravity. Each wavelength of data from this disorganized group reveals something about the limits of the world, and not all of those lessons are simple to fit with theory. At first glance, it might seem that the physics of a cluster merger should be simple. Gravity brings things together, gas collides and heats, galaxies and dark matter follow predictable paths. But the cosmic collision zone has repeatedly defied those expectations. Its overlapping structures, asymmetrical mass distributions, and strange velocity patterns don't fit neatly into simulations based solely on standard cosmological models. Even with the most advanced supercomputers, reproducing the observed features of this cluster has proven nearly impossible without tweaking certain parameters, a clue that either the models are incomplete or this system is showing us a rare but real corner of cosmic behavior that we haven't yet captured. The first clue came from its temperature distribution. X-ray observations from Chandra and XMM Newton show enormous variations across the cluster, with pockets of gas exceeding 200 million kelvins adjacent to regions half that temperature. Standard hydrodynamic simulations predict smoother gradients once shockwaves and turbulence mix the plasma, but here the heat seems uneven and long-lasting. This hints that thermal conduction, the process by which energy flows through the plasma, is being suppressed. The likely culprit is the cluster's magnetic field, which channels heat along narrow filaments rather than letting it spread isotropically. Yet the magnetic field strength required to explain this is far higher than most cosmological models allow. Are magnetic fields stronger or more widespread in the universe than we thought? Or is something about plasma microphysics behaving differently on these scales? Then there's the dark matter distribution. Gravitational lensing maps reveal 4 distinct mass peaks corresponding to the original subclusters, but they're not where theory says they should be. Some are offset from the visible galaxies and plasma, trailing behind the collision rather than leading it. This pattern suggests that dark matter doesn't always behave as a completely collisionless fluid. A few cosmologists have proposed that these offsets could be signs of self-interacting dark matter, SIDM, a variant of dark matter that occasionally scatters off itself rather than passing through cleanly. Even a tiny interaction cross-section could create measurable drags or distortions during cluster collisions. If confirmed, that would transform our understanding of particle physics, implying that dark matter isn't truly inert, but governed by forces beyond gravity. Alternatively, some researchers suggest the offsets might not require exotic matter at all. Perhaps the mismatch arises from modifications to gravity itself. The cosmic collision zone has become a testing ground for modified Newtonian dynamics, MOND, and tensor vector scalar, TVS, theories, which adjust how gravity behaves at large scales or low accelerations. In these models, the observed gravitational lensing and galaxy motions could be explained without invoking dark matter. However, applying them to such a chaotic environment is difficult. So far, the data fit best with a hybrid explanation. Gravity remains Einsteinian, but dark matter has subtle interactions we're only beginning to glimpse. Einstein's general relativity too faces an endurance trial here. On cluster scales, it predicts exactly how mass and energy should curve spacetime and bend light. But the cosmic collision zone's extreme mass and motion push those predictions to their breaking point. Measuring the cluster's lensing distortion with precision allows astronomers to test relativity in a regime far beyond what solar system or binary pulsar experiments can reach. So far, the theory has held. The bending of light matches Einstein's equations within observational error. Yet, the cluster's chaotic structure offers opportunities to probe for even tinier deviations. Future telescopes, like the Nancy Grace Roman Space Telescope and next-generation ground observatories, could measure gravitational lensing distortions at sub% accuracy, potentially revealing cracks in our most successful theory of gravity. It's also not clear how much energy the cluster has. It's hard to believe that the Union produced so much kinetic and thermal energy, enough to power trillions of supernovae, but only a small amount of it can be seen as X-rays or radio waves. The rest must be hiding somewhere, probably in cosmic rays or turbulent movements that our tools can't see. It is very important to know where that lost energy goes because it affects how long the cluster stays hot, how quickly it stabilizes, and how well it gives off radiation. ALMA and MeerKAT observations show that the turbulence stays in place and heats the plasma long after the shocks should have gone away. This suggests that the system's energy loss is much more complicated than was thought before. The cluster also challenges assumptions about entropy, a key property in cosmology used to trace how structure forms and evolves. In theory, as gas collapses under gravity, it should heat and increase in entropy steadily. But measurements of entropy across the cosmic collision zone show irregularities, abrupt jumps, plateaus, and cold pockets embedded within hot regions. These anomalies suggest that mixing and shock heating occur in bursts rather than smoothly, possibly tied to episodic collisions or feedback from active galactic nuclei. Such complexity may require new approaches to modeling how clusters reach thermal equilibrium, or even redefine what equilibrium means in these extreme systems. Adding to the puzzle is how cosmic magnetism works. Radio relics from the cluster that have been studied for polarization show fields that are ordered over millions of light years, which is much more than what turbulence alone should be able to do. Some scientists think that these fields may come from magnetism that was present in the very beginning of the universe and got stronger when the two universes merged. If so, looking at their structure might help us figure out how the first magnetic fields in the universe formed. This is a question that has stumped scientists ever since cosmic magnetism was discovered. From this point of view, the cosmic collision zone is like a time capsule. It holds a record of the early electromagnetic seeds of the universe that have been saved and are now stretched and charged by gravity collapse. Then comes the influence of dark energy, subtle yet significant even here. Over the billions of years that this collision has been unfolding, the expansion of the universe has been accelerating, gradually diluting the density of matter in the surrounding regions. As a result, the cosmic collision zone may be among the last large-scale mergers of its kind. By measuring how fast the subclusters are moving relative to one another and comparing those velocities to cosmological models, scientists can test the influence of dark energy at intermediate redshifts, an observational bridge between the early and late universe. Intriguingly, some of the velocities observed here seem higher than expected, sparking debate over whether dark energy's influence was weaker in the past, or if local gravitational overdensities can temporarily resist its push. The cosmic collision zone embodies the intersection of astrophysics and cosmology, a single structure that tests everything from plasma physics to the geometry of space-time. It demonstrates how gravity, magnetism, and particle physics weave together to shape the universe's largest objects. It also highlights how incomplete our picture still is. For every dataset that fits our equations, another raises questions. Why are the dark matter halos offset? Why hasn't the gas fully mixed? Why do magnetic fields remain coherent? Why do shocks last so long? Each of these questions feeds into the next, forming a chain of mysteries that stretches from the microscopic scale of plasma particles to the cosmic scale of dark energy. This collision is the last test of the universe's rules. It condenses everything we know and don't know into a single event that can be seen. Here, gravity, physics, quantum mechanics, and relativity all work at the same time and interact in ways that can't be found anywhere else. Our ideas can explain a lot of what we see, which is amazing. What's even more interesting is that they still don't explain everything. This means that we can still find new things and learn new things from the universe. The universe never stops teaching us. Even in its most violent moments, the cosmic collision zone shows that from destruction comes understanding and from chaos, clarity. If you enjoyed exploring this journey through space's most extreme battlefield, make sure to like, subscribe, and turn on notifications so you never miss the next discovery. And when you're ready to keep traveling deeper into the cosmos, watch the next video on your screen.